Picture this. You're standing in what is now the barren Badlands of Montana. But 66 million years ago, this landscape told a completely different story. Instead of windswept plains and rocky outcrops, you would have found yourself in a lush, subtropical paradise teeming with life. Towering ferns created dense canopies overhead, while flowering plants carpeted the forest floor in ways that would seem almost alien to us today. The air was thick and humid, filled with the sounds of creatures that ruled this ancient world. But here's what makes this place truly extraordinary. You're not just looking at any prehistoric ecosystem. You're witnessing the final chapter of the dinosaur age, frozen in time through one of the most remarkable fossil formations on our planet. This is the Hell Creek Formation, and it holds secrets that have revolutionized our understanding of life on Earth. What I'm about to share with you isn't just another dinosaur documentary. We're going to dive deep into an ecosystem where the most fearsome predator that ever walked the earth reigned supreme. We're talking about Tyrannosaurus rex, but not the Hollywood monster you think you know. We're going to explore the real T-Rex in its natural habitat, surrounded by the incredible diversity of life that shared its world during those final moments before everything changed forever. By the end of this series, you'll understand exactly how this apex predator fit into one of the most complex and fascinating ecosystems in Earth's history. You'll discover creatures you've never heard of, witness predator-prey relationships that would make modern nature documentaries look tame, and most importantly, you'll see how paleontologists have pieced together this incredible story from fragments of bone and stone. But first, let me tell you why the Hell Creek Formation is unlike any other fossil site in the world. This isn't just some random collection of ancient bones. This formation captures a precise moment in time, spanning roughly the last 2 million years of the Cretaceous Period. That might sound like a long time, but in geological terms, it's the blink of an eye. What makes it even more remarkable is that it preserves not just the giant dinosaurs we all know and love, but an entire ecosystem from microscopic organisms to massive predators. The story begins in the early 20th century when paleontologists first started uncovering fossils in the rugged terrain of the American West. What they found challenged everything scientists thought they knew about prehistoric life. Here was evidence of a world where massive, herbivorous dinosaurs browsed alongside tiny mammals, where ancient crocodiles shared rivers with primitive birds, and where flowering plants were transforming the very nature of terrestrial ecosystems. Stretching across parts of Montana, North Dakota, and South Dakota, the Hell Creek Formation represents what was once a vast floodplain ecosystem. Rivers meandered through dense forests, creating oxbow lakes and swampy wetlands that supported an incredible array of life forms. The climate was dramatically different from today's Great Plains, with temperatures and humidity levels more similar to modern Louisiana or Florida. This wasn't just a tropical paradise, though. This was a world in transition, experiencing dramatic environmental changes that would ultimately lead to one of the most significant mass extinction events in Earth's history. The asteroid impact that would end the age of dinosaurs was approaching, and the Hell Creek Formation captures the ecosystem right up to that pivotal moment. Now, when most people think about Tyrannosaurus rex, They imagine a mindless killing machine stomping through prehistoric forests, roaring at everything in sight. But the real story is far more fascinating than any movie could portray. The T-Rex that lived in the Hell Creek ecosystem was a sophisticated predator, perfectly adapted to its environment and playing a crucial role in maintaining the delicate balance of this ancient world. Standing up to 12 meters long and weighing as much as 9 tons, Tyrannosaurus was indeed the apex predator of its time. But what made it so successful wasn't just its size or its bone-crushing bite. This was an animal with forward-facing eyes that provided excellent depth perception, a highly developed sense of smell that could track prey across vast distances, and surprisingly acute hearing that made it an incredibly effective hunter. Recent discoveries have revealed that T-Rex wasn't the lumbering giant we once imagined. Its powerful leg muscles could propel it at impressive speeds, though probably not in extended high-speed chases. Instead, this predator likely specialized in ambush tactics, using its bulk and devastating bite force to take down large herbivores in sudden, explosive attacks. But here's where the story gets really interesting. Tyrannosaurus didn't hunt alone in this ecosystem. The Hell Creek Formation reveals evidence of a complex predatory hierarchy, with different carnivores filling different ecological niches. Alongside the mighty T-Rex, smaller but equally deadly predators stalk the forests and plains, each adapted to hunt specific types of prey. The herbivores that shared this world with Tyrannosaurus were no less impressive. Massive Triceratops, with their distinctive 3-horned skulls and bony frills, were among the most common large plant eaters. These weren't passive victims either. Evidence from fossil bones shows that Triceratops and other ceratopsians regularly engaged in combat with predators, using their formidable horns and protective armor to defend themselves and their young. Then there were the hadrosaurs, or duck-billed dinosaurs like Edmontosaurus. These remarkable herbivores had developed some of the most sophisticated dental batteries ever seen in the animal kingdom, allowing them to process tough, fibrous plant material with incredible efficiency. Some specimens have been so well preserved that we can actually see impressions of their skin and soft tissues, giving us unprecedented insight into how these animals lived and moved. The plant life of the Hell Creek ecosystem was equally extraordinary. This was a world dominated by flowering plants, or angiosperms, which had recently evolved and were rapidly diversifying. 90% of the plant species found in Hell Creek fossils were flowering plants, a dramatic shift from earlier ecosystems dominated by ferns and conifers. These weren't plants that would look familiar to us today, though. While some fossils bear superficial resemblances to modern species, most represent entirely extinct lineages that experimented with forms and lifestyles we can barely imagine. Palm trees grew alongside ancient relatives of magnolias and water lilies, creating forest compositions unlike anything in the modern world. The rivers and wetlands that crisscrossed this landscape supported their own incredible diversity of life. Freshwater mussels and other mollusks filtered nutrients from the water, while various species of fish, from ancient sturgeons to primitive relatives of modern bowfins, filled every aquatic niche imaginable. What's particularly fascinating about the Hell Creek ecosystem is how it demonstrates the interconnectedness of all life. The massive herbivorous dinosaurs weren't just wandering around eating plants at random. They were ecosystem engineers, shaping the landscape through their feeding behaviors and creating opportunities for other species to thrive. When a Triceratops herd moved through a forest, they would clear undergrowth and create open spaces where different types of plants could establish themselves. Their dung provided fertilizer for the soil, supporting the growth of the very plants they and other herbivores depended on. When these giants died, their massive carcasses became feeding opportunities for predators and scavengers, from the mighty T-Rex down to the smallest mammals and insects. And speaking of smaller creatures, the Hell Creek Formation reveals that this wasn't just a world of giants. Tiny mammals scurried through the underbrush, early birds soared through the canopies, and countless species of insects pollinated flowers and decomposed organic matter. These smaller animals played crucial roles in maintaining the ecosystem's stability and complexity. The preservation of this ancient world is nothing short of miraculous. The specific geological conditions that created the Hell Creek Formation allowed for exceptional fossilization, capturing not just bones and teeth, but also skin impressions, plant materials, and even evidence of behavior and ecological interactions. Paleontologists have found fossilized bite marks on dinosaur bones, providing direct evidence of predator-prey interactions. They've discovered coprolites, or fossilized dung, that reveal what these ancient animals were eating. They've even found evidence of diseases and injuries, showing us that life in the Hell Creek ecosystem could be just as challenging and complex as life in any modern environment. But perhaps most remarkably, the Hell Creek Formation preserves evidence of the very end of this extraordinary world. The boundary between the Cretaceous and Paleogene periods, marked by the asteroid impact that ended the age of dinosaurs, is preserved in these rocks. Scientists can literally point to a thin layer of sediment and say, this is where the dinosaurs' world ended. What makes this even more poignant is the evidence that the Hell Creek ecosystem was thriving right up until that moment. There's no indication that dinosaurs were in decline or that the ecosystem was failing. If anything, the diversity and complexity of life in Hell Creek suggests that dinosaurs and their contemporaries might have continued to evolve and diversify for millions more years, if not for that cosmic catastrophe. This brings us to one of the most important aspects of studying the Hell Creek Formation, understanding extinction and survival. While the asteroid impact ended the reign of non-avian dinosaurs, it didn't wipe out all life. Many species survived the crisis and went on to inherit the post-dinosaur world. Studying which species survived and which didn't provides crucial insights into the nature of mass extinctions and the factors that determine evolutionary success. Small body size, generalized diets, and the ability to shelter underground or underwater seem to have been key survival traits. Meanwhile, large body size and specialized feeding requirements often prove to be evolutionary dead ends. The Hell Creek Formation also demonstrates the importance of understanding ecosystems as integrated wholes rather than just collections of individual species. The relationships between predators and prey, between plants and their pollinators, between decomposers and the organic matter they process, all of these connections were crucial to the functioning of this ancient world. Today, as we face our own environmental challenges, the lessons from Hell Creek become increasingly relevant. This ancient ecosystem shows us what can happen when environmental conditions change rapidly and dramatically. It also shows us the incredible resilience and adaptability of life, and how new opportunities can emerge even from catastrophic change. The techniques that paleontologists use to study Hell Creek continue to evolve and improve. Advanced imaging technologies allow scientists to see inside fossils without damaging them. Chemical analyses can reveal details about ancient climates and diets. Computer modeling helps researchers understand how these ancient animals moved and behaved. Each new discovery adds another piece to the puzzle, helping us build an ever more complete picture of what life was like in this remarkable ecosystem. And there's still so much more to discover. New species are being found and described regularly, and each one adds to our understanding of the complexity and diversity of the Hell Creek world. What emerges from all this research is a picture of an ecosystem that was both alien and familiar. Alien in its cast of characters, with giant predatory dinosaurs and bizarre flowering plants unlike anything alive today, but familiar in its underlying patterns and processes, the same ecological relationships and evolutionary pressures that shape life on Earth today. In our next installment, we're going to zoom in on the star of this ancient drama, Tyrannosaurus rex itself. We'll explore how this ultimate predator was perfectly adapted to its environment, how it hunted and fed, and how it interacted with the other inhabitants of its world. We'll look at the latest scientific discoveries that are revolutionizing our understanding of T-Rex biology and behavior, and we'll see how this iconic dinosaur fits to the broader story of life in the Hell Creek ecosystem. But before we dive deep into the world of T-Rex, we need to understand something crucial about how paleontologists have reconstructed this ancient ecosystem. The Hell Creek Formation isn't just a random collection of fossils scattered across the landscape. It's a carefully preserved library of life, where every bone, every leaf impression, and every trace fossil tells part of a larger story. Think about it this way. Imagine trying to understand modern African savanna ecosystems by only looking at scattered bones and teeth. You'd need to piece together not just what animals lived there, but how they interacted, what they ate, where they made their homes, and how the entire system functioned as a living, breathing community. That's exactly what paleontologists have been doing with Hell Creek for over a century, and the picture they've assembled is absolutely mind-blowing. The fossil record here is so rich and detailed that scientists can actually track changes in the ecosystem over time. They've identified distinct layers within the formation that represent different time periods, allowing them to see how plant and animal communities evolved and changed during those final 2 million years of the Cretaceous Period. What they've discovered challenges many of our assumptions about prehistoric life. For instance, the popular image of dinosaurs living in some kind of primitive, unchanging world couldn't be further from the truth. The Hell Creek ecosystem was dynamic and constantly evolving, with species adapting to changing environmental conditions and new evolutionary pressures. Climate played a massive role in shaping this world. The late Cretaceous was a time of global warming, with atmospheric carbon dioxide levels much higher than today. There were no polar ice caps, and even the Arctic region supported lush forests. The Hell Creek region experienced a subtropical climate with high humidity and abundant rainfall, creating perfect conditions for the diverse plant life that formed the foundation of the entire ecosystem. But here's where it gets really fascinating. This wasn't just a stable tropical paradise. The climate was actually becoming more extreme during the time period preserved in Hell Creek. Evidence from plant fossils shows increasing temperatures and changing precipitation patterns. Some scientists believe these environmental changes may have been stressing ecosystems even before the asteroid impact delivered the final blow. The plant communities that supported this incredible diversity of animal life were unlike anything we see today. Imagine walking through a Hell Creek forest 66 million years ago. The canopy would have been dominated by primitive relatives of modern trees, but mixed in ways that would seem completely alien to us. Ancient magnolias grew alongside early palms and primitive oaks, while the understory was filled with ferns and early flowering shrubs. These plants weren't just passively supporting the ecosystem. They were actively shaping it through complex chemical and physical interactions. Many of the flowering plants had evolved sophisticated relationships with insect pollinators, creating intricate webs of dependency that rippled through the entire food chain. When herbivorous dinosaurs fed on these plants, they weren't just consuming calories. They were participating in complex ecological relationships that affected everything from soil chemistry to forest structure. The diversity of plant life also created a mosaic of different microhabitats within the broader Hell Creek ecosystem. Dense riverside forests provided shelter and food for different species than the more open woodland areas. Wetland margins supported their own specialized communities of plants and animals. Each of these habitat types required different survival strategies and supported different assemblages of species. This habitat diversity is crucial for understanding how Tyrannosaurus rex fit into the Hell Creek world. As the apex predator, T-Rex couldn't survive in isolation. Its success depended entirely on the health and productivity of the entire ecosystem pyramid beneath it. Every plant that grew, every herbivore that fed, every smaller predator that hunted, all of these contributed to maintaining the complex web of relationships that allowed a 9-ton carnivore to thrive. Recent discoveries have revealed just how sophisticated these ecological relationships were. Paleontologists have found evidence of seasonal migration patterns among some dinosaur species, suggesting that different parts of the Hell Creek region supported different communities at different times of year. Some herbivorous dinosaurs may have moved between upland and lowland areas, following the growth patterns of their preferred food plants. This seasonal movement would have had profound implications for predators like Tyrannosaurus. Rather than being a simple sit-and-wait ambush hunter, T-Rex may have needed to be much more strategic about its hunting grounds and timing. Following herds of migrating herbivores would have required intelligence, planning, and possibly even social coordination among individual tyrannosaurs. The evidence for T-Rex social behavior is still hotly debated among paleontologists, but recent discoveries are painting a picture of these predators as much more complex animals than previously imagined. Fossil sites containing multiple tyrannosaur individuals suggest that they may have lived and hunted in small groups, at least under certain circumstances. But social behavior among apex predators brings its own challenges. Multiple T-Rex individuals in the same area would need access to enormous amounts of prey to sustain themselves. This means the Hell Creek ecosystem must have been incredibly productive, supporting not just individual giant predators, but potentially small groups of them. The mathematics of this ecosystem are staggering. A single adult Tyrannosaurus would have needed to consume hundreds of pounds of meat per day to maintain its massive body. Supporting multiple individuals across the Hell Creek region would have required vast herds of herbivorous dinosaurs, which in turn needed enormous quantities of plant matter to sustain themselves. This brings us to one of the most remarkable aspects of the Hell Creek ecosystem, its incredible biomass density. The fossil record suggests that this ancient world supported far more large vertebrates per square kilometer than any modern terrestrial ecosystem. African savannas, with their impressive herds of elephants, giraffes, and antelope, pale in comparison to the sheer mass of animal life that roamed the Hell Creek landscape. How was this possible? The answer lies in the unique combination of climate, plant productivity, and evolutionary innovation that came together during the late Cretaceous. The warm, humid climate supported year-round plant growth. The evolution of flowering plants had created new, highly nutritious food sources, and millions of years of dinosaur evolution had produced herbivores with incredibly efficient digestive systems capable of extracting maximum nutrition from plant matter. The hadrosaurs, or duck-billed dinosaurs, were particularly remarkable in this regard. Their complex dental batteries, containing hundreds of individual teeth arranged in grinding surfaces, allowed them to process tough, fibrous plant material more efficiently than any herbivore before or since. Some species could replace their teeth continuously throughout their lives, maintaining peak digestive efficiency even as they aged. This efficiency created a positive feedback loop in the ecosystem. More efficient herbivores could extract more energy from plants, allowing them to grow larger and support bigger populations. Larger herbivore populations could sustain more and larger predators, and the waste products from all these animals fertilized the soil, supporting even more luxuriant plant growth. The result was an ecosystem operating at maximum capacity, supporting the largest terrestrial predators and herbivores in Earth's history. But this also meant the system was operating near its limits. Any significant disruption could potentially cause the entire structure to collapse, which is exactly what happened when the asteroid struck at the end of the Cretaceous. Understanding these ecological relationships helps explain why the asteroid impact was so devastating. It wasn't just the immediate effects of the collision that caused the mass extinction. The highly interconnected nature of late Cretaceous ecosystems meant that disrupting any part of the system could cascade through the entire web of relationships. When the impact winter blocked sunlight and caused global cooling, plant productivity crashed. This immediately affected herbivorous dinosaurs, which had evolved to depend on abundant, high-quality plant food. As herbivore populations collapsed, the predators that depended on them faced starvation. The entire ecosystem structure that had taken millions of years to evolve unraveled in just a few thousand years. But some components of the Hell Creek ecosystem proved more resilient than others. Small mammals, with their lower metabolic requirements and more generalized diets, were better positioned to survive the crisis. Birds, with their ability to fly and access different food sources, also weathered the extinction better than their non-flying dinosaur relatives. The survival patterns from the Hell Creek extinction provide crucial insights into ecosystem resilience and vulnerability. Large body size, which had been an advantage during the productive late Cretaceous, became a liability when resources became scarce. Specialized feeding requirements, which had allowed different species to coexist by dividing up available resources, became death traps when those specific resources disappeared. These lessons from deep time are increasingly relevant as we face our own environmental challenges. The Hell Creek ecosystem shows us both the incredible complexity that's possible in natural systems and the potential fragility of that complexity when faced with rapid environmental change. Modern paleontologists studying Hell Creek use increasingly sophisticated techniques to understand these ancient ecological relationships. Isotope analysis of fossil bones can reveal what animals were eating and where they lived. Microscopic examination of fossilized plant tissues can show evidence of insect damage and herbivore feeding. Computer modeling can simulate ecosystem dynamics and test hypotheses about how these ancient communities functioned. Each new analytical technique opens up previously invisible aspects of the Hell Creek world. Recent studies using advanced imaging have revealed details about dinosaur growth rates, bone structure, and even possible evidence of feathers and other soft tissues that were previously undetectable. What emerges from all this research is a picture of the Hell Creek ecosystem as one of the most complex and productive terrestrial communities in Earth's history. It was a world where evolution had pushed the boundaries of what was possible for land-based life forms, creating giants that dwarf anything alive today while maintaining the intricate ecological relationships necessary to sustain them. The tragedy and wonder of Hell Creek is that this remarkable world came to an abrupt end just as it was reaching its evolutionary peak. The asteroid impact didn't just kill individual organisms, it destroyed an entire way of organizing terrestrial life that had taken hundreds of millions of years to evolve and can never be recreated. Yet the Hell Creek Formation ensures that this lost world isn't truly lost. Every new fossil discovery adds to our understanding of how this ecosystem functioned. Every new analytical technique reveals previously hidden aspects of ancient life. And every new insight helps us better understand both the history of life on Earth and the ecological principles that govern all living systems. In our next segment, we'll focus specifically on how Tyrannosaurus rex operated as the apex predator in this complex ecosystem. We'll explore the latest discoveries about T-Rex anatomy and behavior, examine the evidence for how it hunted and fed, and investigate its relationships with both prey species and potential competitors. Most importantly, we'll see how even the mightiest predator in Earth's history was completely dependent on the intricate web of ecological relationships that made the Hell Creek world possible. The predatory lifestyle of Tyrannosaurus rex in the Hell Creek ecosystem reveals one of nature's most perfectly engineered killing machines. But not in the way Hollywood would have you believe. This wasn't some mindless monster crashing through forests and terrorizing everything in sight. The real T-Rex was far more sophisticated, far more strategic, and frankly, far more terrifying than any movie could portray. Recent fossil evidence has completely transformed our understanding of how this apex predator operated within its ancient world. We're talking about an animal that combined raw physical power with surprising intelligence, acute senses, and hunting strategies that would make modern predators look primitive by comparison. But here's what makes T-Rex truly remarkable. It didn't just dominate through brute force. It succeeded by being perfectly adapted to exploit every weakness in the Hell Creek ecosystem's complex web of life. Let's start with the physical reality of being a 9-ton predator in a world full of heavily armored prey. Imagine trying to hunt animals the size of city buses that come equipped with their own personal weapon systems. Triceratops wasn't just some oversized rhinoceros. We're talking about an 8-ton herbivore armed with 3 massive horns and protected by a solid bone shield that could deflect almost any attack. Ankylosaurus was basically a living tank, covered in bony armor and wielding a tail club that could shatter bones with a single swing. How do you hunt prey like that? The answer lies in understanding T-Rex as an ambush predator with capabilities that border on the supernatural. Those forward-facing eyes weren't just for show. They provided binocular vision with depth perception that allowed precise targeting of vulnerable spots on heavily defended prey. The massive skull housed a brain with enlarged olfactory bulbs, giving T-Rex a sense of smell that could track injured or sick animals across miles of dense forest. But the real secret weapon was that devastating bite. We're not just talking about big teeth here. The jaw muscles of Tyrannosaurus could generate bite forces exceeding 12,000 pounds per square inch. To put that in perspective, that's enough force to crush a pickup truck. Those banana-sized teeth weren't designed to slash and tear like modern big cats. They were bone crushers, capable of punching through the thickest armor and delivering instantly fatal wounds to the largest prey. The hunting strategy that emerges from fossil evidence is both elegant and terrifying. T-Rex likely operated as a patient stalker, using its acute senses to identify vulnerable targets from considerable distances. Sick animals, juveniles separated from their herds, or adults weakened by injury or old age would have been prime targets. The predator would then use the dense forest cover to approach undetected, positioning itself for a single, devastating ambush attack. When that attack came, it would have been over in seconds. Recent biomechanical studies suggest that T-Rex could accelerate to impressive speeds over short distances, using its massive leg muscles to close the final gap between itself and its prey in an explosive rush. The impact of 9 tons of predator hitting at full speed, followed immediately by that bone-crushing bite, would have been instantly lethal to even the largest herbivores. But successful predation in the Hell Creek ecosystem required more than just raw hunting ability. The fossil record reveals evidence of complex behavioral adaptations that allowed T-Rex to maximize its hunting success, while minimizing energy expenditure and risk of injury. Bite marks on prey bones show evidence of strategic targeting, with T-Rex consistently attacking the most vulnerable areas of its victim's anatomy. Even more fascinating is the evidence for opportunistic scavenging behavior. T-Rex wasn't too proud to steal meals from smaller predators or feed on naturally deceased animals. Those powerful jaws that could crush fresh bone were equally effective at accessing the marrow and nutrients in carcasses that had been dead for days or weeks. This dietary flexibility was crucial for supporting such a massive predator in an ecosystem where successful hunts might be separated by days or weeks. The social dynamics of T-Rex are still hotly debated, but mounting evidence suggests these predators were far more intelligent and socially complex than previously imagined. Fossil sites containing multiple tyrannosaur individuals have been discovered, raising intriguing questions about whether these apex predators might have cooperated in certain circumstances. Imagine the implications of cooperative hunting among Tyrannosaurus. A coordinated attack by multiple 9-ton predators could take down even the largest and most heavily defended herbivores. The strategic possibilities are mind-boggling. While one individual creates a distraction, others could position themselves for flanking attacks. Injured prey trying to escape one predator might run directly into the jaws of another. But cooperation among apex predators comes with its own challenges. Multiple T-Rex individuals in the same territory would require enormous quantities of prey to sustain themselves. The mathematics of predator ecology suggest that the Hell Creek ecosystem must have supported truly staggering numbers of herbivorous dinosaurs to make such social behavior viable. This brings us to one of the most remarkable aspects of T-Rex ecology, its role as an ecosystem engineer. The presence of such a massive apex predator would have shaped the behavior and evolution of every other species in the Hell Creek community. Herbivorous dinosaurs would have been under constant pressure to develop better defenses, more effective group coordination, and enhanced vigilance behaviors. The fossil record provides tantalizing glimpses of this evolutionary arms race. Ceratopsian dinosaurs like Triceratops show evidence of increasingly robust defensive features over time. Horn shapes became more optimized for combat. Frill designs became more effective at protecting vital areas, and body sizes increased to make individual animals more difficult targets. But T-Rex wasn't the only predator shaping this ecosystem. The discovery of Dakotaraptor, a massive dromaeosaurid reaching lengths of over 5 meters, reveals that the Hell Creek Formation supported a complex predatory hierarchy. These smaller but equally deadly hunters filled different ecological niches, targeting different prey species and using different hunting strategies. Dakotaraptor represents a completely different approach to predation. Where T-Rex relied on overwhelming power and bone-crushing bites, these dromaeosaurids were precision killers. Their sickle-shaped claws and lightweight build made them incredibly agile pursuit predators, capable of running down smaller prey or working in packs to overwhelm larger victims. The coexistence of these different predatory strategies within the same ecosystem reveals the incredible productivity and complexity of the Hell Creek world. There was enough prey diversity to support multiple types of large carnivores, each specialized for different hunting scenarios and target species. Smaller predators like Ankylosaurus filled yet another niche, probably specializing in juvenile dinosaurs and smaller prey species that were beneath the notice of the giants. Even these relatively modest predators were formidable hunters in their own right, possessing the intelligence and agility that made dromaeosaurids such successful predators throughout the Cretaceous Period. The aerial dimension of Hell Creek predation adds another layer of complexity to this ancient ecosystem. Pterosaurs, like the newly described Inferno patrolled the skies, using their exceptional eyesight and flight capabilities to spot carrion and small prey from great distances. While not large enough to threaten adult dinosaurs, these flying reptiles played crucial roles as scavengers and predators of smaller vertebrates. Early birds were also beginning to establish their own predatory niches within the Hell Creek ecosystem. Species like Avisaurus show adaptations for grasping and killing prey, suggesting that raptorial birds were already evolving the hunting strategies that would make them so successful in post-extinction ecosystems. This diversity of predatory strategies created a complex web of competition and cooperation that shaped every aspect of life in the Hell Creek world. Smaller predators had to be constantly aware of the threat posed by T-Rex, which would have been quite capable of killing and eating other carnivores if the opportunity arose. Evidence of bite marks on smaller predator fossils confirms that such interactions occurred regularly. But the relationship between different predators wasn't always antagonistic. Smaller carnivores could benefit from the massive kills made by T-Rex, feeding on scraps and accessing parts of carcasses that the giant predator couldn't efficiently utilize. This created opportunities for complex scavenging hierarchies, with different species accessing different parts of the same kill at different times. The seasonal dynamics of the Hell Creek ecosystem added yet another dimension to predatory behavior. Evidence from plant fossils suggests that this region experienced distinct wet and dry seasons, with corresponding changes in plant productivity and herbivore distribution. T-Rex and other predators would have needed to adapt their hunting strategies to these seasonal cycles. During productive wet seasons, when plant growth was abundant and herbivore populations were at their peak, predators might have had the luxury of being selective about their prey choices. But during drier periods, when resources became scarce and herbivore populations declined, even the mighty T-Rex might have been forced to take greater risks and accept less optimal prey. The evidence for this seasonal variation comes from detailed analysis of growth patterns in dinosaur bones. Many Hell Creek dinosaurs show periodic interruptions in their growth, suggesting times of nutritional stress that correspond to seasonal resource limitations. Even apex predators weren't immune to these environmental pressures. Understanding these seasonal dynamics helps explain some of the more puzzling aspects of T-Rex anatomy and behavior. The massive size of these predators might have been partly an adaptation to seasonal feast or famine cycles. Larger body size would have allowed them to store more energy during productive periods and survive longer during times of scarcity. The territorial behavior of T-Rex also becomes more comprehensible when viewed in the context of seasonal resource variation. Individual predators might have maintained large territories that encompassed different habitat types, ensuring access to prey populations even when conditions changed dramatically from season to season. Recent discoveries have also revealed evidence of age-related changes in T-Rex hunting behavior. Juvenile tyrannosaurs had very different body proportions than adults, with longer legs and more gracile builds that suggest a lifestyle focused on pursuit hunting rather than ambush predation. As they grew larger and more powerful, their hunting strategies apparently shifted to emphasize the devastating bite attacks that made adult T-Rex so effective against heavily armored prey. This ontogenetic shift in predatory behavior meant that different age classes of T-Rex were essentially filling different ecological niches within the same ecosystem. Juveniles competed more directly with medium-sized predators like Dakotaraptor, while adults had few competitors for the largest prey species. The implications of this age-based niche partitioning are profound. It meant that a successful T-Rex population could extract resources from multiple levels of the ecosystem simultaneously, with juveniles focusing on smaller prey while adults tackled the giants. This strategy maximized the efficiency with which tyrannosaur populations could exploit available prey resources. But it also created complex intraspecific competition dynamics. Adult T-Rex would have posed a significant threat to juveniles of their own species, forcing young tyrannosaurs to be extremely cautious about their movements and feeding behaviors. Evidence of bite marks on juvenile T-Rex bones suggests that cannibalism was not uncommon, adding another layer of complexity to the social dynamics of these remarkable predators. The feeding behavior of T-Rex reveals fascinating insights into the daily realities of being an apex predator in the Hell Creek ecosystem. Those massive jaws weren't just weapons. They were sophisticated tools for extracting maximum nutrition from each kill. Tooth marks on prey bones show evidence of systematic dismemberment, with T-Rex methodically accessing different parts of carcasses to maximize caloric intake. The bone-crushing ability of T-Rex was particularly important in this context. While other predators might waste the nutritious marrow inside large bones, T-Rex could crack open even the largest femurs and vertebrae to access these high-energy food sources. This ability to utilize parts of carcasses that were inaccessible to other predators gave T-Rex a significant competitive advantage. Coprolite evidence, though rare, provides direct insights into T-Rex diet and digestive processes. These fossilized droppings contain bone fragments that have been ground down to tiny particles, confirming the incredible effectiveness of tyrannosaur digestive systems. The presence of partially digested bone in these fossils also suggests that T-Rex could extract nutrients from bone mineral itself, not just the organic matter within bones. The energetic requirements of maintaining a 9-ton predatory lifestyle in the Hell Creek ecosystem were staggering. Modern calculations suggest that an adult T-Rex would have needed to consume several hundred pounds of meat per day just to maintain its basic metabolic processes. During periods of rapid growth or increased activity, these requirements would have been even higher. Meeting these enormous energy demands required exceptional hunting efficiency. T-Rex couldn't afford to waste energy on unsuccessful hunts or poorly executed attacks. Every aspect of their anatomy and behavior had been refined over millions of years of evolution to maximize hunting success while minimizing energy expenditure. The success of T-Rex as an apex predator ultimately depended on the incredible productivity of the Hell Creek ecosystem. The warm climate, abundant rainfall, and diverse plant communities created the foundation for enormous herbivore populations that could sustain multiple species of large predators. Without this ecological foundation, giants like T-Rex simply couldn't have existed. This dependence on ecosystem productivity also meant that T-Rex was vulnerable to any disruption in the complex web of relationships that sustained the Hell Creek world. When the asteroid impact at the end of the Cretaceous disrupted plant productivity and caused herbivore populations to collapse, even the mightiest predator in Earth's history couldn't survive the resulting ecological cascade. The extinction of T-Rex and its contemporaries marked the end of an extraordinary chapter in the history of life on Earth. Never again would terrestrial ecosystems support predators of such massive size and devastating capability. The unique combination of climate, plant productivity, and evolutionary innovation that made the Hell Creek ecosystem possible was lost forever when that asteroid struck 66 million years ago. But the legacy of T-Rex lives on in the fossil record, providing us with invaluable insights into the principles of predation, ecosystem dynamics, and evolutionary adaptation. Every new discovery adds to our understanding of how these remarkable animals lived, hunted, and shaped the world around them. In our next installment, we'll explore the other side of the predatory equation by examining the incredible diversity of prey species that shared the Hell Creek ecosystem with T-Rex. From the massive, herbivorous dinosaurs that formed the base of the food pyramid to the smaller creatures that filled every available ecological niche, we'll see how this ancient world supported such an extraordinary abundance of life, and how all of these species were ultimately connected in the complex web of relationships that defined one of Earth's most remarkable ecosystems. The herbivorous giants that roamed the Hell Creek landscape weren't just passive victims waiting to become T-Rex's next meal. These were sophisticated, highly evolved creatures that had spent millions of years developing some of the most impressive defensive strategies and feeding adaptations in the history of life on Earth. Understanding these remarkable animals is crucial to grasping how the Hell Creek ecosystem functioned as an integrated whole, because without them, none of the predatory magnificence we've been discussing could have existed. Let's start with the most iconic of these herbivorous titans, Triceratops. When you picture this dinosaur, you probably imagine some kind of prehistoric rhinoceros with a few extra horns. But that mental image doesn't even begin to capture the reality of what Triceratops represented in the Hell Creek ecosystem. We're talking about an animal that could reach 30 feet in length and weigh as much as an African elephant, but armed with weaponry that puts any modern herbivore to shame. Those 3 facial horns weren't decorative accessories. They were precision-engineered combat weapons, each one capable of punching through armor or delivering fatal wounds to attacking predators. The 2 brow horns could grow to over 3 feet in length, while the smaller nasal horn provided additional offensive capability during close-quarters combat. But here's what makes Triceratops truly formidable. These horns were just the beginning of its defensive arsenal. That massive bony frill extending behind the skull wasn't just protection for the neck and shoulders. It was an integrated defensive system that also served as an attachment point for incredibly powerful jaw muscles. Triceratops possessed one of the most sophisticated chewing mechanisms ever evolved, with a sharp beak for cropping vegetation and rows of shearing teeth that could process the toughest plant material with remarkable efficiency. Recent discoveries have revealed just how effective these feeding adaptations were. Fossil evidence shows that Triceratops could consume and digest plant materials that would be completely inedible to modern herbivores. Tough, fibrous vegetation that would break the teeth of contemporary animals was routine fare for these Cretaceous giants. This ability to exploit low-quality food sources gave Triceratops access to vast quantities of plant material that other herbivores couldn't utilize. But feeding efficiency was just one part of the Triceratops success story. These animals were also remarkably social, with evidence suggesting they lived in herds that could number in the hundreds or even thousands of individuals. Imagine the sight of a Triceratops migration. Countless tons of armored herbivores moving across the Hell Creek landscape like a living avalanche. Their synchronized movements creating clouds of dust visible from miles away. The social behavior of Triceratops served multiple functions beyond simple protection from predators. Large herds could collectively modify their environment, clearing vast areas of vegetation and creating new habitat types for other species. Their massive footprints would have created temporary water collection points during rainy seasons, while their dung provided fertilizer that supported entirely different plant communities. This ecosystem engineering role of herbivorous dinosaurs is often overlooked, but it was absolutely crucial to understanding how the Hell Creek world functioned. When a Triceratops herd moved through an area, they didn't just eat plants and move on. They fundamentally altered the landscape, creating opportunities for other species while simultaneously preparing the ground for future plant growth cycles. The defensive capabilities of Triceratops extended far beyond individual combat effectiveness. Herd behavior allowed these animals to present a coordinated defense against predators, with adults forming protective circles around vulnerable juveniles. Fossil evidence of healed bite wounds on Triceratops bones shows that many individuals survived predator attacks, suggesting that their defensive strategies were genuinely effective, even against apex predators like T-Rex. But Triceratops wasn't the only herbivorous giant dominating the Hell Creek landscape. Edmontosaurus, the massive duck-billed dinosaur we mentioned earlier, represented a completely different approach to herbivorous success. Where Triceratops relied on armor and weaponry, Edmontosaurus achieved dominance through sheer feeding efficiency and social coordination. These remarkable creatures possessed what may be the most sophisticated dental system ever evolved by any herbivore. Their jaws contained hundreds of individual teeth arranged in complex batteries that functioned like biological food processors. As teeth wore down from constant use, they were continuously replaced by new ones growing from below, ensuring that Edmontosaurus could maintain peak feeding efficiency throughout their entire lives. The effectiveness of this system is almost beyond comprehension. Edmontosaurus could process tons of plant material per day, extracting nutrients from vegetation that would be completely indigestible to most other animals. This incredible feeding capacity allowed them to achieve massive body sizes, with some individuals reaching lengths of over 40 feet and weights exceeding several tons. But size wasn't the only advantage that Edmontosaurus gained from their feeding efficiency. The ability to quickly process large quantities of low-quality vegetation gave them access to food sources that were effectively unlimited in the Hell Creek ecosystem. While other herbivores might compete intensely for high-quality plants, Edmontosaurus could thrive on abundant but nutritionally poor vegetation that other animals ignored. This feeding strategy had profound implications for Hell Creek ecosystem dynamics. Edmontosaurus populations could reach enormous sizes because they weren't limited by competition for premium food sources. Fossil evidence suggests that these duck-billed giants may have been the most abundant large herbivores in the Hell Creek ecosystem, forming vast herds that migrated seasonally across the landscape. The social behavior of Edmontosaurus reveals fascinating parallels with modern herd animals. Evidence suggests they communicated using low-frequency vocalizations that could travel for miles, allowing separated groups to maintain contact across vast distances. Their hollow crests may have functioned as resonating chambers, amplifying these calls and allowing for complex acoustic communication within herds. Seasonal migration patterns among Edmontosaurus would have created dramatic pulses of herbivore abundance in different parts of the Hell Creek ecosystem. During certain times of year, areas that seemed relatively empty would suddenly be filled with thousands of these massive herbivores, fundamentally altering local plant communities and creating temporary feeding opportunities for predators and scavengers. The impact of these migrations on Hell Creek plant communities would have been revolutionary. Areas subjected to intensive Edmontosaurus grazing would have been transformed from dense forests into more open woodland or grassland habitats. This habitat modification created niches for entirely different assemblages of plants and animals, increasing the overall diversity of the ecosystem. But the herbivorous diversity of Hell Creek extended far beyond these two dominant giants. Ankylosaurus represented perhaps the ultimate expression of defensive evolution, taking the concept of protective armor to its logical extreme. These walking fortresses were covered from head to tail in thick, bony plates, with additional spikes and knobs protecting every vulnerable area of their anatomy. The defensive strategy of Ankylosaurus was fundamentally different from that of Triceratops. Where ceratopsians relied on active defense using horns and coordinated herd behavior, Ankylosaurs were essentially mobile bunkers. Their low-slung bodies and comprehensive armor made them nearly invulnerable to most predator attacks, while their massive tail clubs could deliver devastating counterattacks against any predator foolish enough to get too close. Recent biomechanical studies have revealed just how effective these tail weapons would have been. The club at the end of an Ankylosaurus tail could generate impact forces sufficient to shatter bones, and the precision with which these animals could aim their strikes suggests sophisticated neural control systems. This wasn't random flailing. It was targeted, deadly accurate defensive weaponry. The lifestyle implications of carrying such comprehensive armor were significant. Ankylosaurus had to be selective about their habitat choices, avoiding areas where their low mobility might become a liability. They probably preferred relatively open environments where their armor provided maximum advantage and their limited speed wouldn't be as much of a disadvantage. This habitat specialization meant that Ankylosaurus filled a unique ecological niche within the Hell Creek ecosystem. They could exploit food sources in areas that were too dangerous for other herbivores, while their defensive capabilities allowed them to browse calmly even in areas with high predator density. In many ways, they represented the herbivorous equivalent of a tank division, able to operate effectively in hostile territory where other species couldn't survive. The smaller herbivorous dinosaurs of Hell Creek were no less remarkable in their own ways. Thescelosaurus, though modest in size compared to the giants we've been discussing, possessed adaptations that allowed it to thrive in ecological niches that larger animals couldn't exploit. Its lightweight build and efficient locomotion made it ideally suited for life in dense forest environments, where maneuverability was more important than size or armor. The feeding strategy of Thescelosaurus reveals fascinating insights into the complexity of Hell Creek plant communities. These smaller herbivores were browsers rather than bulk feeders. selectively targeting high-quality plant parts like young shoots, fruits, and tender leaves. This feeding specialization meant they weren't competing directly with the giant herbivores, instead exploiting food sources that were too scattered or small-scale to interest larger animals. But perhaps the most intriguing aspect of Thescelosaurus ecology was their apparent ability to exploit seasonal changes in plant productivity. Evidence suggests these animals were capable of dramatic shifts in their feeding behavior, switching between different plant types as seasonal availability changed. This dietary flexibility would have been crucial for survival in an ecosystem where resource availability could vary dramatically from season to season. The pachycephalosaurs, or dome-headed dinosaurs, represent another fascinating example of herbivorous specialization in the Hell Creek ecosystem. Species like Pachycephalosaurus and Stygimoloch, which may actually represent different growth stages of the same species, possessed unique skull adaptations that have puzzled paleontologists for decades. Those distinctive dome-shaped skulls were once thought to be weapons used in head-butting contests, similar to modern bighorn sheep. But recent research suggests a more complex picture. The dome structure may have supported elaborate soft tissue displays, functioning more as visual signals than combat weapons. The social implications of this are fascinating. These animals may have relied more on display and intimidation than actual physical combat to establish dominance hierarchies. The feeding ecology of Pachycephalosaurs reveals another layer of specialization within Hell Creek herbivore communities. Their small, leaf-shaped teeth suggest a diet focused on soft vegetation, possibly including fruits and seeds that were becoming increasingly common as flowering plants diversified. This dietary specialization meant they were exploiting food sources that were largely ignored by the bulk-feeding giants. The ceratopsian diversity in Hell Creek extended beyond just Triceratops. Torosaurus, with its distinctive open-frilled skull structure, may represent either a separate species or a mature form of Triceratops. The debate continues among paleontologists. Regardless of its exact taxonomic status, the presence of ceratopsians with different frill morphologies suggests that even within successful herbivore groups, there was ongoing evolutionary experimentation with defensive strategies. Leptoceratops represents the other end of the ceratopsian size spectrum, demonstrating that not all horned dinosaurs were giants. These smaller relatives of Triceratops lacked the impressive horns and frills of their larger cousins, instead relying on speed and agility to escape predators. Their success in the Hell Creek ecosystem shows that there were viable alternatives to the armor and weapons approach favored by larger ceratopsians. The coexistence of these different herbivorous strategies within the same ecosystem reveals the incredible productivity and habitat diversity of the Hell Creek world. There was enough plant biomass and sufficient habitat variety to support multiple approaches to herbivorous success, from the armored titans to the swift browsers to the efficient bulk processors. But understanding Hell Creek herbivores requires looking beyond just the dinosaurs. The ecosystem also supported a remarkable diversity of other plant-eating vertebrates, each filling specialized niches that contributed to the overall complexity of the community. Freshwater turtles like Trionyx and Aspidoretes exploited aquatic plant resources, while various species of mammals browsed on different types of terrestrial vegetation. The multituberculate mammals were particularly important components of Hell Creek herbivore communities. Species like Mesodma possessed specialized teeth adapted for processing seeds and nuts, allowing them to exploit food sources that were largely inaccessible to larger animals. Their small size and high metabolic rates meant they could survive on scattered high-energy food items that wouldn't sustain larger herbivores. These mammalian herbivores also played crucial ecological roles as seed dispersers. Unlike the giant dinosaurs, which probably destroyed most seeds they consumed, small mammals could transport viable seeds across considerable distances, helping to maintain genetic connectivity among plant populations. This ecosystem service would have been essential for maintaining the diversity and resilience of Hell Creek plant communities. The seasonal dynamics of herbivore communities in Hell Creek would have been spectacular to witness. During peak growing seasons when plant productivity was at its maximum, the landscape would have been filled with enormous herds of dinosaurs, each species exploiting different aspects of the abundant vegetation. The biomass density during these productive periods may have exceeded anything seen in modern terrestrial ecosystems, but seasonal variation also created periods of resource limitation that tested the survival strategies of different herbivore species. During dry seasons or periods of reduced plant growth, competition for available vegetation would have intensified dramatically. Only the most efficient feeders and those with access to specialized food sources would have been able to maintain their populations through these challenging periods. The evidence for these seasonal bottlenecks comes from detailed analysis of growth patterns in herbivore bones. Many Hell Creek dinosaurs show periodic interruptions in their growth, suggesting times when nutrition was limited and energy had to be redirected from growth to basic survival. These growth interruptions were probably synchronized across multiple species, indicating ecosystem-wide periods of resource scarcity. Understanding these seasonal dynamics helps explain some of the more puzzling aspects of Hell Creek herbivore evolution. The enormous sizes achieved by many species may have been partly an adaptation to seasonal feast or famine cycles. Larger body size would have allowed animals to store more energy during productive periods and survive longer during times of scarcity. The migration patterns that many herbivore species probably followed would have created complex spatial and temporal patterns of resource use across the Hell Creek landscape. Different areas would have experienced pulses of intense herbivore pressure, followed by periods of recovery, creating a constantly shifting mosaic of habitat conditions that supported different assemblages of plants and animals. These migration patterns also had profound implications for predator ecology. Predators like T-Rex would have needed to time their own movements to coincide with herbivore migrations, following the herds to maintain access to prey. The ability to predict and respond to these seasonal movements would have been crucial for predator survival. The plant communities that supported this incredible diversity of herbivores were themselves remarkably complex and dynamic. The Hell Creek ecosystem was dominated by flowering plants, representing one of the first terrestrial communities where angiosperms had achieved ecological dominance. This transition from earlier fern and conifer-dominated ecosystems to angiosperm-dominated communities had profound implications for herbivore evolution. Flowering plants offered new types of food resources that hadn't been available in earlier ecosystems. Fruits, nectar, and specialized seed structures provided high-energy food sources that could support different feeding strategies. The coevolution between flowering plants and their herbivore consumers drove rapid diversification in both groups, creating the complex web of plant-herbivore interactions that characterized Hell Creek ecosystems. The chemical defenses employed by Hell Creek plants added another layer of complexity to herbivore ecology. Many flowering plants had evolved sophisticated chemical compounds designed to deter herbivory, forcing herbivores to develop counter-adaptations to deal with these toxins. This evolutionary arms race between plants and herbivores drove much of the innovation we see in Hell Creek herbivore feeding systems. Some herbivores became specialists, evolving the ability to detoxify specific plant chemicals and exploit food sources that were unavailable to other species. Others became generalists, developing robust digestive systems that could handle a wide variety of potentially toxic compounds. Both strategies were successful in the Hell Creek ecosystem, contributing to the remarkable diversity of herbivore species. The gut microbiome of Hell Creek herbivores would have been incredibly important for processing the diverse array of plant chemicals they encountered. Recent research on modern herbivores has shown that gut bacteria play crucial roles in breaking down plant toxins and extracting nutrients from difficult-to-digest vegetation. The herbivorous dinosaurs of Hell Creek probably harbored complex microbial communities that were essential for their feeding success. The coprolite evidence we have from Hell Creek herbivores provides fascinating insights into these ancient digestive processes. Fossilized dung contains partially digested plant fragments that reveal details about herbivore diets and digestive efficiency. Some coprolites contain intact seeds, suggesting that at least some herbivores were serving as seed dispersers despite their enormous size. The social feeding behaviors of Hell Creek herbivores created complex group dynamics that influenced everything from individual survival to ecosystem-level patterns of resource use. Evidence suggests that many species fed in coordinated groups, with different individuals taking turns as sentries while others focused on feeding. This cooperative behavior would have been essential for survival in an ecosystem with such formidable predators. The communication systems that supported these social behaviors were probably quite sophisticated. Large herbivores need effective ways to coordinate group movements and warn of approaching dangers. The variety of skull crests and other display structures seen in Hell Creek herbivores suggests that visual communication was important, while evidence for vocal communication indicates that acoustic signals also played crucial roles. The juveniles of herbivorous dinosaur species faced particularly complex challenges in the Hell Creek ecosystem. Not only did they have to avoid predators that specialized in targeting young animals, but they also had to compete for food resources while their feeding apparatus was still developing. Growth patterns in juvenile fossils suggest that young herbivores had access to different food sources than adults, probably exploiting softer, more easily digested vegetation. This age-related dietary specialization meant that single herbivore species were actually exploiting multiple ecological niches simultaneously, with different age classes utilizing different resources. Juveniles might browse on tender shoots and fruits, while adults processed tough, fibrous vegetation. This niche partitioning reduced intraspecific competition and allowed herbivore populations to achieve higher densities than would otherwise be possible. The reproductive strategies of Hell Creek herbivores had to be perfectly adapted to the seasonal cycles of resource availability. Evidence suggests that many species timed their reproduction to coincide with periods of maximum plant productivity, ensuring that rapidly growing juveniles had access to high-quality nutrition. The synchronization of reproductive cycles with environmental conditions would have created dramatic pulses in juvenile abundance that rippled through the entire ecosystem. Nest sites and nesting behaviors had to balance the need for protection with access to food resources. Some herbivores probably nested in areas that were relatively safe from predators, but required adults to travel considerable distances to reach feeding areas. Others may have nested closer to food sources, but accepted higher predation risks. These different strategies created spatial patterns of reproductive success that influenced population dynamics across the landscape. The extinction event that ended the Cretaceous period had devastating impacts on Hell Creek herbivore communities, but the patterns of survival and extinction reveal important insights about ecosystem resilience. Larger herbivores with specialized dietary requirements were generally more vulnerable than smaller, more generalized feeders. This suggests that dietary flexibility and reduced resource requirements were crucial survival traits during periods of environmental crisis. The collapse of herbivore populations during the end Cretaceous extinction created cascading effects throughout the Hell Creek ecosystem. As the primary consumers disappeared, the entire food web structure that had supported such remarkable diversity began to unravel. The loss of ecosystem engineers like the giant herbivorous dinosaurs also meant that many of the habitat modifications they had created could no longer be maintained. But some elements of Hell Creek herbivore communities did survive the extinction event. Small mammals and other vertebrates with generalized diets and modest resource requirements weathered the crisis and went on to inherit the post-extinction world. These survivors carried forward genetic and ecological legacies from the Hell Creek ecosystem that continue to influence terrestrial communities today. The study of Hell Creek herbivores provides crucial insights into the principles of herbivore ecology that remain relevant for understanding modern ecosystems. The relationships between body size and resource requirements, the importance of dietary specialization versus generalization, and the role of social behavior in herbivore survival are all themes that connect these ancient communities to contemporary ecological systems. In our final segment, we'll explore how the complex web of relationships we've been describing, from apex predators to herbivorous giants to the countless smaller creatures that filled every available niche, came together to create one of the most remarkable ecosystems in Earth's history, and how that entire world was transformed by the catastrophic events that marked the end of the Cretaceous Period. The smaller inhabitants of the Hell Creek ecosystem were far from insignificant players in this ancient drama. While the giants dominated the landscape through sheer size and spectacle, it was often the creatures we might overlook that kept the entire system functioning. These were the unsung heroes of the Cretaceous world, filling every conceivable ecological niche and creating the intricate connections that allowed such massive biodiversity to flourish in a single region. Let's dive into the aquatic realm first, because the rivers and wetlands of Hell Creek supported their own incredible communities of life. Picture these ancient waterways teeming with activity that would put modern freshwater ecosystems to shame. We're talking about rivers filled with fish species that had been perfecting their survival strategies for millions of years, some of which still have descendants swimming in our waters today. The sturgeons of Hell Creek represent one of the most remarkable success stories in vertebrate evolution. These ancient fish had already been around for over 100 million years by the time T-Rex was stalking the landscape, and they were so well adapted to their environment that they barely needed to change. Some specimens found in Hell Creek deposits are virtually identical to modern sturgeons, demonstrating an evolutionary stability that spans the entire age of dinosaurs. But here's what makes these ancient sturgeons truly fascinating. They were living witnesses to the entire history of dinosaur evolution. While species of massive predators and herbivores rose and fell around them, these fish just kept doing what they'd always done, filtering nutrients from river sediments and growing to impressive sizes in the process. Some Hell Creek sturgeon fossils suggest individuals that would have rivaled the largest specimens alive today. The paddlefish that shared these waters with the sturgeons were equally remarkable, though for completely different reasons. These bizarre-looking creatures had evolved one of the most sophisticated sensory systems in the aquatic world, using their elongated rostrums as electrical detection devices. Those paddle-like snouts weren't just for show. They were packed with electroreceptors that could detect the faintest electrical fields generated by other organisms. Imagine the underwater world these paddlefish inhabited. Every movement of every creature in the water would have created electrical signatures that these ancient fish could read like a book. Injured animals would have generated different electrical patterns than healthy ones. Schools of smaller fish would have created complex electrical landscapes that paddlefish could navigate with incredible precision. This was biological radar that puts our modern technology to shame. The diversity of freshwater fish in Hell Creek waters extended far beyond these ancient lineages. Bowfins, with their primitive but effective predatory adaptations, filled the role of apex aquatic hunters. Some specimens reached lengths of over 6 feet, making them formidable predators, capable of taking prey as large as young dinosaurs that ventured too close to the water's edge. These aquatic predators weren't just passive inhabitants of the Hell Creek ecosystem. They were active participants in the complex web of relationships that connected terrestrial and aquatic communities. When dinosaurs came to drink at the water's edge, they entered a world where different rules applied, where creatures that seemed insignificant on land could pose serious threats to even large terrestrial animals. The freshwater mussels and other mollusks that carpeted the river bottoms were performing ecosystem services that were absolutely crucial to maintaining water quality. These filter feeders were processing enormous quantities of water every day, removing particles and nutrients that could have made the aquatic environment uninhabitable for other species. Without them, the crystal-clear streams that supported such diverse fish communities simply couldn't have existed. But the aquatic realm wasn't limited to fish and mollusks. Hell Creek waters also supported an incredible diversity of reptiles that had adapted to semi-aquatic lifestyles. Crocodilians were particularly successful, with multiple species filling different ecological niches within the same river systems. Some were specialized fish eaters with narrow snouts and sharp teeth, while others were generalist predators capable of taking anything from fish to dinosaurs. The survival of these crocodilian lineages through the end Cretaceous extinction event provides important clues about the factors that determined which species weathered the crisis. Their semi-aquatic lifestyle gave them access to food sources that remained available even when terrestrial ecosystems collapsed. Their ability to regulate their metabolism and survive long periods without food proved crucial when resources became scarce. Moving from the aquatic realm to the forest floor, we encounter another whole dimension of Hell Creek biodiversity. The amphibians of this ancient ecosystem were far more diverse than anything we see in modern temperate environments. Salamanders reached sizes that would seem impossible today, with some species growing to lengths of over 5 feet. These weren't just scaled-up versions of modern salamanders. They were entirely different creatures with unique adaptations to their Cretaceous environment. The largest of these ancient salamanders had evolved feeding strategies that allowed them to take prey as large as small dinosaurs. Their crushing bite force and robust skull construction suggest they were capable of processing hard-shelled prey that would be completely inaccessible to modern amphibians. This represents a level of ecological versatility that demonstrates just how different late Cretaceous ecosystems were from anything we see today. The frogs of Hell Creek were equally remarkable, though in completely different ways. Some species had evolved fully aquatic lifestyles, spending their entire lives in water and developing morphological adaptations that paralleled those of modern aquatic frogs. Others were terrestrial specialists, with robust limbs and specialized feeding apparatus that allowed them to exploit food sources in the dense forest understory. What's particularly fascinating about Hell Creek amphibians is their role as indicators of ecosystem health. Modern amphibians are extremely sensitive to environmental changes, and there's every reason to believe their ancient relatives shared this sensitivity. The diversity and abundance of amphibian fossils in Hell Creek deposits suggests that water quality and environmental conditions were consistently favorable throughout the time period represented by the formation. The reptile diversity of Hell Creek extended far beyond the dinosaurs and crocodilians we've already discussed. Lizards filled an incredible array of ecological niches, from tiny insectivores that hunted among the leaf litter to large predatory species that competed directly with small dinosaurs. Some of these ancient lizards reached sizes that dwarf their modern relatives, demonstrating once again how the productive Hell Creek environment supported larger body sizes across multiple groups. The snakes of Hell Creek represent some of the earliest examples of these remarkable predators in the fossil record. While they hadn't yet evolved the sophisticated venom systems or constriction abilities of their modern descendants, they were already demonstrating the flexibility and predatory effectiveness that would make snakes one of the most successful vertebrate groups on the planet. Turtles were particularly abundant and diverse in Hell Creek ecosystems, with species adapted to virtually every available aquatic and semi-aquatic niche. Soft-shelled turtles reached enormous sizes, with some specimens suggesting individuals that would have weighed hundreds of pounds. These aquatic giants were perfectly adapted to the productive freshwater environments of the Hell Creek world, using their powerful jaws and sharp beaks to process a wide variety of prey. But it wasn't just the aquatic turtles that were impressive. Terrestrial species had evolved their own remarkable adaptations to life in the Hell Creek ecosystem. Some had developed incredibly thick shells that provided protection against the formidable predators that roamed the landscape. Others had evolved specialized feeding apparatus that allowed them to process tough vegetation that other herbivores couldn't utilize. The survival of turtle lineages through the end Cretaceous extinction provides another example of how ecological flexibility contributed to evolutionary success. Their ability to withdraw into protective shells, combined with relatively modest metabolic requirements, allowed many turtle species to survive environmental conditions that proved fatal to larger, more specialized animals. Moving up into the forest canopy, we encounter the early birds and pterosaurs that were competing for aerial niches in the Hell Creek ecosystem. This was a world where flight was still relatively new, and different groups were experimenting with various approaches to aerial locomotion and lifestyle. The diversity of flying creatures in Hell Creek reveals just how quickly evolution was proceeding during this remarkable period. The early birds of Hell Creek were far from the small, delicate creatures we might imagine. Some species had evolved into formidable predators, with sharp talons and powerful beaks that allowed them to take prey as large as small mammals and juvenile dinosaurs. These raptorial birds were already demonstrating the hunting strategies that would make birds of prey so successful in post-extinction ecosystems. But not all Hell Creek birds were predators. Some had evolved specialized feeding adaptations that allowed them to exploit resources that were unavailable to other creatures. Diving birds with tooth-lined beaks were perfectly adapted to catching fish in the productive aquatic environments, while others had developed filtering mechanisms that allowed them to strain small organisms from the water. The pterosaurs that shared the Hell Creek skies with these early birds represented an entirely different approach to powered flight. These flying reptiles had been perfecting their aerial adaptations for over 100 million years, and by the late Cretaceous, they had achieved sizes and capabilities that seem almost impossible by modern standards. The largest pterosaurs found in Hell Creek deposits suggest wingspans that would have rivaled small aircraft. These weren't just gliders riding air currents. They were powered flyers capable of covering vast distances and exploiting resources across enormous areas. Their presence in Hell Creek ecosystems demonstrates that aerial niches were just as competitive and diverse as terrestrial ones. The feeding strategies employed by Hell Creek pterosaurs were remarkably varied. Some were fish eaters, using their long beaks and excellent eyesight to snatch prey from the water's surface. Others were terrestrial stalkers, hunting small vertebrates in the dense forest understory. Still others may have been scavengers, using their flight capabilities to locate and access carcasses across wide areas. The mammalian diversity of Hell Creek provides perhaps the most poignant glimpse into the future of terrestrial ecosystems. These small, furry creatures were already demonstrating many of the adaptations that would make mammals the dominant vertebrate group in post-dinosaur environments. Yet, during the Cretaceous, they were still living in the shadows of the great reptilian dynasties. The multituberculate mammals that scurried through Hell Creek forests had evolved some of the most sophisticated dental systems ever developed by any mammalian group. Their complex tooth arrangements allowed them to process seeds, nuts, and other hard plant materials with remarkable efficiency. This dietary specialization gave them access to food sources that were largely unavailable to other small vertebrates. Some multituberculate species had evolved climbing adaptations that allowed them to exploit arboreal niches in the Hell Creek forest canopy. These early tree dwellers were pioneering ecological strategies that would eventually be perfected by primates and other mammalian groups millions of years later. Their presence in Hell Creek demonstrates that mammals were already experimenting with the diverse lifestyles that would characterize their post-extinction radiation. The carnivorous mammals of Hell Creek were equally innovative, though in completely different ways. Some had evolved semi-aquatic lifestyles, using their swimming abilities and specialized dentition to hunt fish and other aquatic prey. Others were terrestrial predators that competed directly with small dinosaurs for similar prey resources. What's particularly remarkable about Hell Creek mammals is their apparent ability to coexist with dinosaurs without direct competition. They had carved out ecological niches that were largely ignored by larger reptilian species, exploiting food sources and habitat types that weren't accessible to dinosaurs. This niche partitioning allowed both groups to thrive in the same ecosystems without significant conflict. The insect diversity of Hell Creek, while poorly preserved in the fossil record, was probably staggering. Evidence from plant fossils shows extensive insect damage, indicating that complex plant-insect relationships were already well established by the late Cretaceous. The evolution of flowering plants had created entirely new ecological opportunities for insects, driving rapid diversification in both groups. Pollinating insects were particularly important in Hell Creek ecosystems, facilitating the reproduction of the flowering plants that dominated the landscape. The coevolution between insects and angiosperms was driving innovation in both groups, creating the complex pollination systems that continue to support terrestrial ecosystems today. Decomposer insects played equally crucial roles in Hell Creek ecosystem function. The enormous quantities of organic matter produced by giant herbivorous dinosaurs had to be broken down and recycled, and insects were probably the primary agents of this decomposition process. Without them, Hell Creek ecosystems would have been buried under accumulating organic debris. The social insects of Hell Creek were already experimenting with the complex colonial behaviors that make modern ants and termites such successful groups. Evidence suggests that some species had evolved sophisticated communication systems and division of labor that allowed them to exploit resources more efficiently than solitary species. Predatory insects filled their own important niches in Hell Creek food webs. Dragonflies reached enormous sizes, with some species achieving wingspans that would dwarf their modern relatives. These aerial hunters were perfectly adapted to exploit the abundant insect prey that filled Hell Creek skies, while their aquatic larvae were equally effective predators in freshwater environments. The plant diversity that supported all of this animal life was itself incredibly complex and dynamic. Hell Creek plant communities were dominated by flowering plants that were still in the early stages of their evolutionary radiation. This was a world where plants were rapidly experimenting with new forms, new reproductive strategies, and new chemical defenses. The trees that formed Hell Creek forest canopies were unlike anything in modern forests. Ancient magnolia relatives grew alongside primitive palms and early members of families that would eventually produce oaks and maples. The combinations of species and the forest structures they created had no modern analogs, representing unique experiments in terrestrial ecosystem organization. Understory plants were equally innovative, with early representatives of many modern families already demonstrating the specialized adaptations that would make them successful in different environmental conditions. Some had evolved sophisticated chemical defenses to protect themselves from herbivory, while others had developed alternative strategies based on rapid growth and reproduction. The aquatic plants of Hell Creek were pioneering the colonization of freshwater environments that had previously been dominated by algae and primitive plant groups. Early water lilies and related species were establishing the foundation for the complex aquatic plant communities that would characterize post-Cretaceous freshwater ecosystems. The seasonal dynamics of Hell Creek plant communities created temporal patterns of resource availability that influenced every other component of the ecosystem. Different plant species flowered and fruited at different times, creating a constantly shifting mosaic of available resources that different animal species had to track and exploit. The chemical ecology of Hell Creek plants was probably incredibly complex, with different species producing various compounds designed to attract pollinators, deter herbivores, or compete with other plants. The evolution of these chemical systems was driving corresponding adaptations in animal species, creating intricate webs of chemical communication that connected all levels of the ecosystem. The preservation of Hell Creek plant fossils provides unprecedented insights into ancient ecosystem function. Leaf fossils show evidence of insect damage that reveals details about herbivore feeding preferences and population densities. Pollen and spore assemblages document seasonal changes in plant community composition. Even fossilized wood provides information about ancient climate conditions and forest structure. The transition from Hell Creek plant communities to post-extinction floras illustrates the profound impact of the end Cretaceous event on terrestrial ecosystems. The immediate aftermath of the asteroid impact is marked by a dramatic spike in fern spores, indicating the temporary collapse of angiosperm-dominated communities and their replacement by pioneer species adapted to disturbed environments. This fern spike represents one of the most dramatic ecosystem collapses documented in the fossil record. Within a matter of years or decades, plant communities that had taken millions of years to evolve were replaced by simple assemblages of rapidly growing pioneer species. The recovery of complex plant communities took thousands of years, and when they did recover, they looked very different from what had existed before. The microbial communities that supported Hell Creek ecosystems were probably as complex and important as those in any modern environment, though they're virtually invisible in the fossil record. Soil bacteria and fungi were essential for nutrient cycling and plant growth, while aquatic microorganisms formed the base of freshwater food webs. The symbiotic relationships between plants and microorganisms were probably crucial for ecosystem function in Hell Creek environments. Mycorrhizal fungi would have been essential partners for many plant species, helping them extract nutrients from soil and resist environmental stresses. These partnerships were probably just as important in ancient ecosystems as they are in modern ones. Nitrogen-fixing bacteria were probably essential for maintaining soil fertility in Hell Creek ecosystems. The enormous biomass of herbivorous dinosaurs would have created significant demands for plant productivity, which could only be sustained through efficient nitrogen cycling. The microbial communities that supported this cycling were invisible but absolutely essential components of the ecosystem. The food webs that connected all of these organisms into integrated ecosystems were incredibly complex, with energy and nutrients flowing through multiple pathways that connected terrestrial, aquatic, and aerial components. Decomposition processes were particularly important, as the enormous quantities of organic matter produced by giant herbivores had to be efficiently recycled to maintain ecosystem productivity. Seasonal patterns of death and decomposition would have created pulses of nutrient availability that rippled through entire food webs. The death of a single large dinosaur would have provided feeding opportunities for numerous scavenger species, while also contributing nutrients to soil communities that supported plant growth. The migration patterns of various animal species created spatial connections between different parts of the Hell Creek ecosystem. Nutrients and energy were transported across the landscape by moving animals, creating complex patterns of resource distribution that influenced local community structure. Disease and parasitism were probably important factors regulating population sizes and community structure in Hell Creek ecosystems, just as they are in modern environments. Evidence of healed injuries and pathological conditions in dinosaur fossils suggests that disease was a significant factor in ancient ecosystems, though the specific pathogens and parasites are rarely preserved. The climate variations that characterized the late Cretaceous created temporal patterns of environmental stress that tested the resilience of Hell Creek communities. Seasonal droughts, floods, and temperature fluctuations would have created selection pressures that drove continued evolution and adaptation in all ecosystem components. The approach of the end Cretaceous extinction event would have been invisible to the organisms living in Hell Creek ecosystems. There were no obvious signs that this incredibly diverse and productive world was about to come to an abrupt end. If anything, the diversity and complexity of life in Hell Creek suggests that terrestrial ecosystems were reaching new heights of evolutionary achievement. The asteroid impact that ended this remarkable world was a cosmic accident that had nothing to do with the success or failure of Hell Creek ecosystems. These communities weren't declining or showing signs of instability. They were thriving right up until the moment when extraterrestrial catastrophe brought their story to a sudden close. The extinction patterns that followed the impact reveal important insights about ecosystem resilience and vulnerability. Small body size, generalized diets, and the ability to survive in disturbed environments proved to be crucial survival traits. Meanwhile, large body size, specialized feeding requirements, and dependence on stable environmental conditions often proved fatal. The survivors of the Hell Creek extinction carried forward genetic and ecological legacies that continue to influence modern ecosystems. The mammals, birds, and other groups that weathered the crisis went on to diversify and fill many of the ecological roles that had been vacated by extinct dinosaur groups. But the specific ecosystem structure and function that characterized Hell Creek was lost forever. Never again would terrestrial environments support such enormous biomass densities or such complex food webs dominated by giant vertebrates. The unique combination of climate, evolution, and ecological innovation that made Hell Creek possible was a one-time experiment that can never be repeated. The study of Hell Creek ecosystems provides crucial insights into the principles of ecology, evolution, and extinction that remain relevant for understanding modern environmental challenges. The lessons learned from this ancient world help us appreciate both the resilience and fragility of complex ecosystems and the importance of preserving the biodiversity that has evolved over millions of years. The techniques used to reconstruct Hell Creek ecosystems continue to evolve, with new analytical methods revealing previously hidden aspects of ancient life. Each technological advance opens new windows into this lost world, allowing us to build ever more detailed pictures of how these remarkable communities functioned. The Hell Creek Formation stands as one of the most important paleontological resources on Earth, preserving the final chapter of the age of dinosaurs in unprecedented detail. Every fossil discovered adds to our understanding of this crucial period in Earth's history, when terrestrial life achieved heights of diversity and complexity that have never been equaled. The story of Hell Creek is ultimately a story about the incredible creativity of evolution and the complex beauty of natural ecosystems. It reminds us that our planet has supported forms of life and ecological relationships that surpass anything in our imagination, and that the diversity of life we see around us today represents just one chapter in a much larger story. As we face our own environmental challenges, the lessons from Hell Creek become increasingly relevant. This ancient ecosystem shows us what's possible when conditions are right for life to flourish, but also demonstrates how quickly complex systems can collapse when faced with catastrophic change. The balance between resilience and vulnerability that characterized Hell Creek continues to shape ecosystems today. The legacy of Hell Creek lives on in the descendants of its survivors, in the ecological principles that still govern natural systems, and in the fossil record that preserves this remarkable world for future generations to study and appreciate. The tyrant king and his ancient kingdom may be gone, but their story continues to teach us about the wonder and complexity of life on Earth. The interconnected web of relationships that made the Hell Creek ecosystem function reveals something profound about the nature of life itself. When you really dig into how this ancient world operated, you start to realize that every creature, from the mightiest Tyrannosaurus down to the smallest beetle, was completely dependent on countless other species for its survival. This wasn't just a collection of animals and plants sharing the same space. This was a living machine of staggering complexity, where the removal of any single component could send ripples of change throughout the entire system. Think about the mathematics of it all. A single adult Tyrannosaurus needed to consume hundreds of pounds of meat every day just to maintain its massive body. That means each T-Rex required a steady supply of herbivorous dinosaurs, which in turn needed access to enormous quantities of plant matter. But here's where it gets really interesting. Those plants depended on specific soil conditions, particular climate patterns, and complex relationships with fungi and bacteria that we're only beginning to understand. The soil itself was a living ecosystem within an ecosystem. Every footstep of every giant dinosaur compressed and aerated the earth, in ways that affected drainage patterns and nutrient distribution. When these massive herbivores died, their decomposing bodies released tremendous quantities of nitrogen and phosphorus back into the soil, fertilizing the very plants that would feed the next generation of giants. But the nutrient cycling in Hell Creek went far beyond simple decomposition. The dung produced by herds of Triceratops and Edmontosaurus wasn't just waste material. It was a crucial component of ecosystem function, providing fertilizer for plants while also creating microhabitats for countless smaller organisms. Dung beetles and other decomposer insects broke down these massive deposits, releasing nutrients in forms that plants could readily absorb. The timing of these processes was absolutely critical. Plant growth had to coincide with optimal weather conditions. Herbivore reproduction had to align with periods of maximum food availability. Predator hunting strategies had to adapt to seasonal changes in prey behavior and distribution. Everything was synchronized in ways that required millions of years of evolutionary fine-tuning. The water cycle in Hell Creek was equally complex and crucial. The massive bodies of dinosaurs contained enormous quantities of water that had to be constantly replenished. Rivers and wetlands weren't just drinking sources. They were highways for nutrient transport, breeding grounds for countless species, and climate regulators that moderated temperature and humidity across the entire region. When herds of giant dinosaurs congregated around water sources, they created temporary but intense impacts on local environments. The trampling of thousands of feet would reshape riverbanks and create new channels. The concentrated waste from large herds would temporarily alter water chemistry. These disturbances weren't destructive. They were part of the natural rhythm of ecosystem function. The forest structure of Hell Creek was constantly being modified by its inhabitants. Large herbivores didn't just eat plants randomly. They were selective feeders with preferences that created patchy patterns of vegetation across the landscape. Areas of intense browsing pressure would open up forest canopies, allowing different types of plants to establish themselves in the increased sunlight. These browsing patterns created what ecologists call a shifting mosaic of habitat types. At any given time, the Hell Creek landscape contained areas in different stages of ecological succession, from recently disturbed clearings to mature forest stands. This habitat diversity was essential for supporting the incredible variety of species that called this ecosystem home. The communication networks that connected Hell Creek organisms were sophisticated beyond our imagination. Chemical signals traveled through soil and air, carrying information about everything from food availability to predator presence. Visual displays conveyed complex social information between individuals and species. Acoustic communication allowed coordination across vast distances. The low-frequency calls of giant dinosaurs could travel for miles through dense forest, allowing separated groups to maintain contact and coordinate movements. These vocalizations weren't just simple contact calls. Evidence suggests they carried complex information about individual identity, emotional state, and environmental conditions. But communication in Hell Creek extended far beyond just sounds and visual displays. Chemical communication was probably even more important. though it's much harder to detect in the fossil record. Plants released compounds that attracted specific pollinators while deterring herbivores. Animals marked territories and communicated reproductive status through scent. Even the soil contained chemical gradients that provided information to organisms capable of detecting them. The predator-prey relationships that we've discussed weren't simple games of cat and mouse. They were sophisticated evolutionary dances where each participant was constantly adapting to counter the strategies of the other. When herbivores developed better armor, predators evolved more powerful jaws. When prey animals improved their group coordination, predators developed more effective hunting strategies. These evolutionary arms races weren't just happening between predators and prey. They were occurring throughout the entire ecosystem. Plants and herbivores were locked in constant evolutionary competition, with plants developing better chemical defenses while herbivores evolved more effective detoxification systems. Pollinators and flowers were co-evolving increasingly specialized relationships that benefited both partners. The energy flow through Hell Creek ecosystems was incredibly efficient, but it required constant maintenance and adjustment. Dead plant material had to be broken down quickly to prevent the accumulation of organic debris that could disrupt ecosystem function. Nutrients had to be recycled rapidly to support the enormous productivity required to maintain such large animal populations. The decomposer organisms that made this rapid recycling possible were probably the most diverse component of Hell Creek ecosystems, even though they're virtually invisible in the fossil record. Bacteria, fungi, and countless species of invertebrates worked together to break down organic matter and release nutrients back into the system. Without their constant activity, the entire ecosystem would have ground to a halt. The seasonal rhythms that governed Hell Creek life created predictable patterns that organisms could exploit, but also periodic challenges that tested survival strategies. During productive wet seasons, resources were abundant and competition was relatively relaxed. But during dry periods, every organism faced intense pressure to find scarce food and water. These seasonal bottlenecks were probably crucial for maintaining ecosystem balance. They prevented any single species from becoming so abundant that it overwhelmed available resources. They also created selection pressures that drove continued evolution and adaptation, ensuring that Hell Creek organisms remained well adapted to their changing environment. The migration patterns that many Hell Creek animals probably followed created temporal connections between different parts of the ecosystem. Nutrients and energy were transported across the landscape by moving herds, creating complex spatial patterns of resource availability. Areas that seemed resource poor during certain seasons would suddenly become incredibly productive when migrating herds arrived. These migrations also created opportunities for different types of ecological interactions. Predators could follow migrating herds, accessing prey populations that would otherwise be unavailable. Scavengers could exploit the carcasses left behind by unsuccessful predators or animals that died during long journeys. Even plants benefited from migrations through seed dispersal and fertilization from animal waste. The genetic diversity that characterized Hell Creek populations was probably enormous, though it's difficult to measure directly from fossil evidence. Large, widespread populations with complex social structures and extensive gene flow would have maintained high levels of genetic variability that provided raw material for continued evolution. This genetic diversity was crucial for ecosystem stability. When environmental conditions changed, genetically diverse populations could adapt more readily than uniform ones. The genetic variation present in Hell Creek populations probably allowed them to respond to the gradual climate changes that were occurring throughout the late Cretaceous period. The disease ecology of Hell Creek was probably as complex as that of any modern ecosystem. Evidence of pathological conditions in dinosaur fossils suggests that infectious diseases were common, but most individuals were apparently able to survive and recover from infections. This indicates that Hell Creek animals had well-developed immune systems, and that disease pressure wasn't overwhelming. Parasites were probably incredibly diverse and abundant in Hell Creek ecosystems, though direct evidence is rare in the fossil record. The warm, humid climate would have been ideal for many types of parasitic organisms, and the dense populations of large animals would have provided ample opportunities for parasite transmission. The coevolutionary relationships between parasites and their hosts would have been driving constant evolutionary change in both groups. Hosts would have been under pressure to develop better immune responses, while parasites would have been evolving strategies to evade those defenses. These invisible evolutionary battles were probably just as intense as the more obvious predator-prey relationships. The pollution tolerance of Hell Creek organisms was probably quite different from that of modern species. The atmosphere contained much higher levels of carbon dioxide, while volcanic activity was creating periodic inputs of various gases and particles. Organisms had evolved in these conditions and were presumably well adapted to them. But this also meant that Hell Creek ecosystems might have been particularly vulnerable to novel types of environmental disruption. When the asteroid impact introduced completely unprecedented atmospheric conditions, organisms that had evolved in stable greenhouse climates had no evolutionary experience with the type of rapid cooling and atmospheric chemistry changes that followed the impact. The recovery patterns after local disturbances in Hell Creek probably followed predictable sequences, with pioneer species quickly colonizing disturbed areas and gradually being replaced by more competitive species as conditions stabilized. These successional processes would have been constantly occurring across the landscape as different areas experienced fires, floods, and other natural disturbances. The resilience of Hell Creek ecosystems to normal disturbances was probably quite high. Millions of years of evolution had produced communities that could recover from periodic disruptions and maintain their basic structure and function. This resilience made the catastrophic nature of the end Cretaceous extinction even more remarkable. The productivity measurements we can estimate for Hell Creek ecosystems suggest levels of primary production that exceeded anything seen in modern terrestrial environments. The combination of warm temperatures, high atmospheric carbon dioxide, and abundant moisture created ideal conditions for plant growth. This high productivity supported the enormous biomass of animals that characterized Hell Creek communities. But high productivity also meant high energy demands throughout the ecosystem. Every component had to function efficiently to maintain the flow of energy and nutrients that kept the entire system operating. Any disruption that reduced primary productivity would have had cascading effects throughout the food web. The spatial organization of Hell Creek ecosystems created complex patterns of resource distribution and habitat quality across the landscape. River valleys supported different communities than upland areas. Forest edges had different species assemblages than forest interiors. Wetland margins provided unique habitat conditions that supported specialized organisms. These spatial patterns weren't static. They changed seasonally as water levels fluctuated and plant phenology shifted. They also changed over longer time scales as rivers meandered, forests matured, and climate conditions evolved. The organisms living in Hell Creek had to be able to track and respond to these spatial and temporal changes. The information flow through Hell Creek ecosystems was probably incredibly rapid and accurate. Organisms needed current information about resource availability, predator presence, and environmental conditions to make appropriate behavioral decisions. The communication networks that provided this information were probably as sophisticated as anything we see in modern ecosystems. Social learning was probably important for many Hell Creek species, particularly the more intelligent dinosaurs. Young animals would have learned crucial survival skills by observing and imitating adults. This cultural transmission of information would have allowed populations to adapt to changing conditions more rapidly than genetic evolution alone would permit. The stress physiology of Hell Creek organisms had to be finely tuned to allow appropriate responses to different types of challenges. Chronic stress from resource limitation or predator pressure had to be balanced against the metabolic costs of stress responses. The organisms that were most successful in Hell Creek had probably evolved optimal stress response systems. The thermoregulation challenges faced by Hell Creek animals were significant, particularly for the largest species. Giant dinosaurs had to maintain appropriate body temperatures despite their enormous size and the warm climate conditions. This required sophisticated physiological and behavioral adaptations that we're still trying to understand. The sensory ecology of Hell Creek was incredibly rich, with different species evolving specialized sensory capabilities that allowed them to detect specific types of environmental information. The acute vision of predators, the chemical detection abilities of herbivores, and the vibrational sensitivity of ground-dwelling animals all contributed to the complex information networks that connected ecosystem components. The sleep and activity patterns of Hell Creek organisms created temporal niches that reduced competition and allowed more species to coexist in the same area. Diurnal and nocturnal species could exploit the same resources at different times, while crepuscular species were active during the transition periods when both day and night species were less active. The reproductive ecology of Hell Creek species was probably incredibly diverse, with different groups employing various strategies for ensuring reproductive success. Some species probably produced large numbers of offspring with minimal parental care, while others invested heavily in fewer offspring with extended parental investment. These different strategies created different patterns of population dynamics and resource use. The developmental biology of Hell Creek organisms had to accommodate the enormous size ranges that characterized many species. The growth rates required to transform tiny hatchlings into massive adults were unprecedented in modern terrestrial animals. Understanding how these developmental processes worked provides insights into the physiological capabilities that made Hell Creek ecosystems possible. The aging processes in Hell Creek animals were probably quite different from those in modern species. The enormous sizes achieved by many dinosaurs suggest that they had evolved mechanisms for maintaining cellular function and structural integrity over extended lifespans. Some individuals may have lived for centuries, accumulating knowledge and experience that benefited their populations. The wound healing and immune responses of Hell Creek animals had to be extremely effective to allow survival in an environment filled with dangerous predators and potential sources of infection. Evidence of healed injuries in dinosaur fossils suggests that even severe wounds could be survived, indicating sophisticated physiological repair mechanisms. The biomechanical constraints that shaped Hell Creek organisms created trade-offs between different functional capabilities. Animals optimized for speed sacrificed strength, while those built for power gave up agility. These biomechanical trade-offs created opportunities for different species to specialize in different ecological roles. The extinction selectivity patterns from the end Cretaceous event reveal which characteristics were most important for surviving catastrophic environmental change. Small body size, dietary generalization, and the ability to shelter or hibernate proved crucial for weathering the crisis. Meanwhile, large body size, dietary specialization, and dependence on stable environments were often fatal. The recovery patterns after the extinction show how ecosystems rebuild after catastrophic collapse. The initial survivors were mostly small, generalized species that could exploit the simplified post-extinction environment. Only gradually did more complex communities develop as environmental conditions stabilized and new evolutionary innovations accumulated. The lessons from Hell Creek about ecosystem function and resilience remain relevant for understanding modern environmental challenges. The complexity and interconnectedness that made Hell Creek so productive also made it vulnerable to cascading collapse when key components were disrupted. This pattern of high productivity coupled with high vulnerability may characterize many modern ecosystems as well. The technological advances that allow us to study Hell Creek continue to reveal new aspects of this ancient world. Each analytical breakthrough opens new windows into ecosystem function and reveals previously hidden connections between different components of these complex communities. The Hell Creek Formation represents one of the most complete records of ecosystem structure and function available anywhere in the geological record. The exceptional preservation and diversity of fossils provide unparalleled opportunities to understand how complex ecosystems operate and how they respond to environmental change. The interdisciplinary approaches required to understand Hell Creek ecosystems bring together expertise from paleontology, ecology, geology, chemistry, and many other fields. This collaborative approach reveals insights that no single discipline could achieve alone, demonstrating the value of integrative research in understanding complex natural systems. The educational value of Hell Creek research extends far beyond academic circles. This ancient ecosystem provides compelling examples of evolutionary processes, ecological relationships, and environmental change that help people understand the natural world and our place within it. The conservation implications of Hell Creek research are profound. Understanding how past ecosystems functioned and why they collapsed provides crucial insights for protecting modern biodiversity and maintaining ecosystem services that human societies depend upon. The Hell Creek ecosystem stands as a testament to the incredible creativity of evolutionary processes and the remarkable complexity that can emerge from natural selection operating over millions of years. It reminds us that our planet has supported forms of life and ecological relationships that surpass our wildest imagination. The story of Hell Creek is ultimately a story about both the power and the fragility of life on Earth. It shows us what's possible when conditions are right for biodiversity to flourish, but also demonstrates how quickly even the most successful ecosystems can be brought to an end by catastrophic change. As we face our own environmental challenges, the lessons from Hell Creek become increasingly relevant. This ancient world teaches us about the importance of preserving the complex ecological relationships that sustain life on our planet, and reminds us that the diversity and beauty of the natural world are both precious and fragile. The legacy of the Hell Creek ecosystem lives on in the fossil record, in the descendants of its survivors, and in the ecological principles that continue to govern life on Earth. Though Tyrannosaurus and its ancient kingdom are gone forever, their story continues to inspire and educate us about the wonder and complexity of the natural world. The final moments of the Hell Creek ecosystem were approaching, though none of its inhabitants could have possibly known what was coming. While Tyrannosaurus rex continued to stalk through the subtropical forests and Triceratops herds thundered across the floodplains, a massive asteroid was hurtling through space on a collision course with Earth. This wasn't some gradual decline or slow environmental shift. The Hell Creek world was about to experience the most catastrophic event in the history of complex life. What makes this impending disaster even more tragic is that the Hell Creek ecosystem was operating at peak efficiency right up until the moment of impact. Recent discoveries have shown that dinosaur diversity was actually increasing in the final million years of the Cretaceous Period. New species were evolving, ecosystems were becoming more complex, and life was experimenting with forms and relationships that had never existed before. The asteroid that would end this remarkable world measured roughly 6 miles in diameter and was traveling at speeds that defy comprehension. When it struck the Yucatan Peninsula 66 million years ago, it released energy equivalent to billions of nuclear weapons detonating simultaneously, but the immediate blast was just the beginning of a chain reaction that would transform every ecosystem on the planet. Within minutes of impact, massive earthquakes rippled across North America. The Hell Creek region located over 1,000 miles from the impact site, would have experienced seismic activity more powerful than any earthquake in recorded human history. Trees that had stood for centuries would have been toppled in seconds. Rivers would have changed course instantly. The very landscape would have been reshaped in moments. But the earthquakes were nothing compared to what came next. The impact had vaporized enormous quantities of rock and water, launching them high into the atmosphere. This superheated material began raining back down across the planet as glass spherules and molten droplets. The Hell Creek forests, already damaged by seismic activity, now faced a bombardment of material hot enough to ignite anything combustible. Within hours, wildfires were spreading across the continent. The dense, humid forests that had supported such incredible biodiversity became death traps as flames consumed everything in their path. Animals that had survived millions of years of evolution, predators that had dominated their ecosystems for eons, found themselves fleeing fires that moved faster than they could run. The atmospheric effects of the impact were even more devastating than the immediate physical destruction. The asteroid had punched through sedimentary rocks rich in sulfur compounds, launching millions of tons of sulfur dioxide into the upper atmosphere. This material began forming aerosol particles that blocked incoming sunlight, initiating what scientists call an impact winter. For organisms that had evolved in the greenhouse climate of the late Cretaceous, this sudden cooling was catastrophic. Temperatures dropped by 20 degrees Celsius or more within weeks of the impact. The subtropical paradise of Hell Creek was transformed into something resembling a nuclear winter, with freezing temperatures and perpetual twilight. But perhaps the most devastating effect was the collapse of photosynthesis. With sunlight blocked by atmospheric debris, plants could no longer produce the energy that formed the foundation of every food web. The incredibly productive plant communities that had supported enormous populations of herbivorous dinosaurs began dying within weeks of the impact. The cascade of ecosystem collapse that followed was swift and merciless. Herbivorous dinosaurs, with their enormous energy requirements, were the first to suffer. Massive Edmontosaurus herds that had numbered in the thousands dwindled to scattered individuals desperately searching for any remaining vegetation. Triceratops groups that had dominated the landscape for millions of years found themselves competing for scraps of dead plant material. The predators that had ruled the Hell Creek ecosystem faced an even more dire situation. As herbivore populations crashed, the prey base that supported carnivores like Tyrannosaurus simply evaporated. These apex predators, which had required hundreds of pounds of meat per day to survive, found themselves in a world where their prey species were dying faster than they could hunt them. The first Tyrannosaurus individuals to succumb were probably the juveniles and subadults, whose smaller body sizes made them less capable of surviving extended periods without food. The massive adults, with their ability to store more energy, may have lasted weeks or even months longer. But eventually, even the mightiest predators in Earth's history fell victim to starvation. The smaller predators fared little better. Dakotaraptor and other dromaeosaurids, despite their intelligence and agility, couldn't overcome the simple mathematics of ecosystem collapse. When the herbivore populations that formed their primary prey base disappeared, these sophisticated hunters had nowhere to turn. Their specialized predatory adaptations, which had made them so successful in the complex Hell Creek ecosystem, became liabilities in the simplified post-impact world. The aquatic environments of Hell Creek provided some refuge from the immediate effects of the impact, but they couldn't escape the broader ecosystem collapse. Fish populations initially survived better than terrestrial animals, but as dead plant and animal material washed into rivers and lakes, water quality deteriorated rapidly. Oxygen levels plummeted as decomposing organic matter consumed available dissolved oxygen. Even the ancient lineages that had survived previous extinction events found themselves overwhelmed by the scope of environmental change. Sturgeons and paddlefish that had weathered the rise and fall of countless dinosaur species couldn't adapt quickly enough to the rapidly changing aquatic conditions. Many populations crashed, though some refugia allowed certain lineages to survive. The crocodilians that had seemed so resilient faced their own challenges as aquatic ecosystems collapsed. Their ability to survive long periods without food proved crucial, but even these hardy survivors were pushed to their limits. Only the smallest species with the most generalized diets managed to weather the crisis, and even they barely hung on in greatly reduced numbers. The plant communities that had taken millions of years to evolve were among the first casualties of the impact winter. The flowering plants that had dominated Hell Creek ecosystems were particularly vulnerable because they required consistent energy input for their complex reproductive systems. As photosynthesis ground to a halt, these sophisticated plants began dying en masse. The fossil record preserves direct evidence of this botanical catastrophe in what paleontologists call the fern spike. Immediately after the impact layer, plant fossil assemblages are dominated by fern spores, indicating that these hardy pioneer species temporarily replaced the complex angiosperm communities that had characterized pre-impact ecosystems. This fern spike represents one of the most dramatic ecological transitions documented in the fossil record. Within decades, plant communities that had supported the most complex terrestrial ecosystems in Earth's history were replaced by simple assemblages dominated by a few resilient species. The intricate relationships between plants and their pollinators, herbivores, and other partners were severed permanently. The insects that had been so crucial to Hell Creek ecosystem function faced their own extinction crisis. The collapse of flowering plant communities eliminated the food sources and habitat for countless specialized species. Pollinating insects, which had co-evolved complex relationships with specific plant species, found themselves without partners. The loss of these relationships created a cascade of extinctions that rippled through entire insect communities. Social insects like ants and termites, despite their sophisticated colonial organization, couldn't overcome the loss of their primary food sources. The wood and plant material they depended on became increasingly scarce as forests died and weren't replaced. Even their ability to store food and work cooperatively couldn't compensate for the complete transformation of their environment. The decomposer insects that had been so important for nutrient cycling found themselves overwhelmed by the quantities of dead organic matter produced by ecosystem collapse. While initially this might have seemed like a bonanza, the sheer volume of decaying material and the altered chemical conditions created by atmospheric changes made normal decomposition processes impossible. The mammals of Hell Creek, despite their small size and presumed adaptability, faced severe challenges during the extinction crisis. Many specialized species, particularly the multituberculates that had evolved sophisticated dietary adaptations, found their food sources eliminated by plant community collapse. The seeds and nuts they depended on simply weren't being produced by dying plant communities. However, the generalized feeding habits of some mammalian species proved crucial for survival. Animals that could switch between different food sources, consume carrion, or even cannibalize members of their own species had better chances of weathering the crisis. The most successful survivors were probably omnivorous species that could exploit any available organic matter. The burrowing abilities that many mammals possessed became life-saving adaptations during the impact winter. Underground refugees provided protection from temperature extremes and may have offered access to stored food resources like roots and buried seeds. The mammals that survived the Hell Creek extinction were probably those that could effectively utilize these underground sanctuaries. The early birds of Hell Creek faced a complex set of challenges during the extinction event. Their ability to fly gave them advantages in searching for scattered food resources, but their high metabolic rates made them vulnerable to prolonged food shortages. The species that survived were probably those with the most flexible dietary requirements and the most efficient metabolisms. Diving birds that could access aquatic food sources had some advantages over purely terrestrial species, but even aquatic environments were severely disrupted by the extinction event. The fish and invertebrate populations that formed the base of aquatic food webs were collapsing just as dramatically as terrestrial communities. The pterosaurs that had dominated Hell Creek skies for millions of years found their aerial lifestyle becoming a liability rather than an advantage. Their large size and specialized feeding requirements made them particularly vulnerable to ecosystem collapse. The largest species, with wingspans rivaling small aircraft, required enormous quantities of food that simply weren't available in the post-impact world. The turtles of Hell Creek demonstrated the survival value of their conservative lifestyle and protective shells. Their ability to reduce metabolic rates and survive long periods without food proved crucial during the extinction crisis. Many turtle lineages that had coexisted with dinosaurs for millions of years managed to survive the impact and continue to modern times. The amphibians of Hell Creek, despite their sensitivity to environmental change, showed surprising resilience during parts of the extinction event. Their ability to utilize both aquatic and terrestrial resources gave them flexibility that purely terrestrial animals lacked. However, many of the largest and most specialized species still succumb to the severity of environmental change. The lizards and snakes of Hell Creek faced challenges similar to other small reptiles. Their ectothermic metabolism made them vulnerable to the temperature changes associated with impact winter, but their relatively modest energy requirements gave them some advantages over larger animals. The most generalized feeders had the best chances of finding alternative food sources as ecosystems collapsed. The marine reptiles that occasionally ventured into Hell Creek freshwater systems were among the casualties of the extinction event. These specialized predators, already restricted to specific aquatic environments, couldn't adapt quickly enough to the rapid changes in water chemistry and prey availability that followed the impact. The extinction patterns that emerged from the Hell Creek catastrophe reveal important insights about survival during mass extinction events. Body size was one of the most important factors, with smaller animals generally having better survival chances than larger ones. This size selectivity explains why dinosaurs, as the dominant large vertebrates, suffered such devastating losses, while smaller mammals and birds fared better. Dietary specialization proved to be another crucial factor determining survival. Animals with narrow, specialized diets were much more vulnerable than generalists that could switch between different food sources. The complex feeding relationships that had made Hell Creek ecosystems so sophisticated became death traps when those relationships were severed by environmental change. Geographic distribution also influenced survival chances. Species with wide geographic ranges and multiple populations had better odds than those restricted to limited areas. The Hell Creek region, despite its incredible diversity, was just one part of a larger continental ecosystem, and species that existed elsewhere had refugia that local specialists lacked. The ability to enter dormant states or reduce metabolic activity proved enormously valuable during the extinction crisis. Animals that could hibernate, estivate, or otherwise reduce their energy requirements could survive longer periods of resource scarcity. This explains why many turtle, crocodilian, and mammal lineages survived while most dinosaur groups went extinct. Underground lifestyle became a crucial survival strategy during the impact winter. Animals that could burrow or utilize underground refugia were protected from temperature extremes and had access to resources that surface-dwelling animals couldn't reach. The mammals that inherited the post-extinction world were predominantly species with fossorial or semi-fossorial lifestyles. The recovery of ecosystems after the Hell Creek extinction took millions of years and followed predictable patterns. The first communities to establish themselves were dominated by rapidly reproducing pioneer species that could quickly colonize disturbed environments. These simple communities gradually gave way to more complex assemblages as environmental conditions stabilized. The mammals that survived the extinction underwent rapid evolutionary diversification in the post-dinosaur world. Freed from competition with giant reptilian predators and herbivores, mammalian lineages quickly evolved to fill vacant ecological niches. Within 10 million years of the extinction, mammals had produced species ranging from tiny shrews to elephant-sized herbivores. The birds that weathered the extinction crisis also diversified rapidly in the New World. Modern bird groups began appearing within a few million years of the impact, taking advantage of ecological opportunities created by the extinction of pterosaurs and non-avian dinosaurs. The aerial niches that had been dominated by flying reptiles were quickly colonized by evolving bird lineages. The plant communities that replaced the Hell Creek flora were fundamentally different from what had existed before. While flowering plants remained dominant, the specific families and ecological relationships that characterize pre-impact communities were largely lost. New plant-animal partnerships had to evolve from scratch, creating ecosystems that functioned differently from their predecessors. The biogeochemical cycles that had supported Hell Creek ecosystems were severely disrupted by the extinction event and took millennia to reestablish. The massive die-offs created enormous pulses of nutrients that temporarily altered soil and water chemistry. These chemical changes had cascading effects on surviving organisms and influenced the trajectory of ecosystem recovery. The climate recovery after the impact winter was gradual and uneven. While global temperatures eventually returned to pre-impact levels, the specific climatic conditions that had supported Hell Creek ecosystems were never recreated. The unique combination of high atmospheric carbon dioxide, warm temperatures, and specific precipitation patterns that had made the Cretaceous greenhouse world possible was gone forever. The evolutionary innovations that had made Hell Creek organisms so successful became evolutionary dead ends when environmental conditions changed catastrophically. The sophisticated dental batteries of hadrosaurs, the massive body sizes of sauropods, and the bone-crushing abilities of Tyrannosaurs were all adaptations to specific ecological conditions that no longer existed. The co-evolutionary relationships that had driven much of the diversity in Hell Creek ecosystems were severed permanently by the extinction event. Plant-insect partnerships that had taken millions of years to develop were lost when either partner went extinct. These broken relationships had to be rebuilt from scratch during ecosystem recovery, often involving completely different groups of organisms. The information stored in Hell Creek fossil assemblages provides crucial data for understanding how ecosystems respond to catastrophic change. The detailed record of community structure before, during, and after the extinction event offers insights into ecosystem resilience and vulnerability that remain relevant for understanding modern environmental challenges. The technological advances that allow modern paleontologists to study Hell Creek continue to reveal new aspects of the extinction event. High-resolution dating techniques can pinpoint the timing of extinctions with unprecedented precision. Chemical analyses can detect environmental changes that occurred over time frames of years or even seasons. The interdisciplinary research required to understand the Hell Creek extinction brings together expertise from multiple scientific fields. Paleontologists work with atmospheric scientists to understand impact effects. Geologists collaborate with ecologists to interpret ecosystem responses. This collaborative approach reveals insights that no single discipline could achieve alone. The conservation implications of Hell Creek research are profound and urgent. Understanding how past ecosystems collapsed provides crucial insights for protecting modern biodiversity. The patterns of extinction and survival documented in Hell Creek offer guidance for identifying which current species and ecosystems are most vulnerable to environmental change. The Hell Creek extinction demonstrates that even the most successful and complex ecosystems can be destroyed by sufficiently severe environmental perturbation. No amount of evolutionary sophistication or ecological complexity can guarantee survival when faced with truly catastrophic change. This sobering lesson reminds us of the fragility of the natural world we depend upon. The speed of the Hell Creek collapse challenges our assumptions about ecosystem stability and resilience. Communities that had maintained their basic structure for millions of years were transformed beyond recognition within decades of the asteroid impact. This rapid transformation illustrates how quickly complex systems can reach tipping points beyond which recovery becomes impossible. The legacy of the Hell Creek extinction extends far beyond the immediate loss of dinosaurs and their contemporaries. The event fundamentally altered the trajectory of life on Earth, eliminating evolutionary lineages that had dominated terrestrial ecosystems for over 100 million years. The modern world we inhabit is largely a product of the evolutionary opportunities created by this ancient catastrophe. The story of Hell Creek serves as both inspiration and warning for our contemporary world. It demonstrates the incredible creativity and resilience of life while simultaneously illustrating how vulnerable complex systems can be to rapid environmental change. As we face our own environmental challenges, the lessons from this ancient ecosystem become increasingly relevant and urgent. The Hell Creek Formation preserves one of the most complete records of ecosystem collapse and recovery available anywhere in the geological record. This extraordinary archive continues to yield new insights about the nature of extinction and survival, the dynamics of ecosystem change, and the long-term consequences of environmental catastrophe. The research techniques developed to study Hell Creek have applications far beyond paleontology. Methods for reconstructing ancient ecosystems inform conservation biology. Approaches for understanding extinction patterns contribute to biodiversity protection efforts. The analytical tools created for studying deep-time environmental change help us understand modern climate systems. The educational value of Hell Creek research extends throughout society, from elementary school students learning about dinosaurs to policymakers grappling with environmental legislation. The compelling story of this ancient ecosystem and its dramatic end provides powerful examples of scientific concepts that might otherwise remain abstract. The Hell Creek ecosystem represents both the pinnacle of dinosaur evolution and its tragic end. Never before or since has our planet supported terrestrial communities of such complexity and dominated by such magnificent creatures. The loss of this remarkable world reminds us that evolutionary success, no matter how spectacular, offers no guarantee against the unpredictable forces that shape life on Earth. The continuing study of Hell Creek ensures that this lost world will not be forgotten. Each new fossil discovery adds to our understanding of how these remarkable ecosystems functioned and why they collapsed. Each analytical breakthrough reveals previously hidden aspects of ancient life. Each insight gained from studying this vanished world helps us better understand the natural systems that sustain us today. The Hell Creek Formation stands as one of paleontology's greatest treasures, preserving the final chapter of the Age of Dinosaurs in unprecedented detail. The tyrant king and his ancient subjects may be gone forever, but their story continues to educate and inspire us about the wonder, complexity, and fragility of life on our remarkable planet. Through studying their world, we gain not only scientific knowledge, but also perspective on our own place in the continuing story of life on Earth. The Hell Creek Formation stands today as our most complete window into this vanished world, but it's so much more than just a collection of ancient bones scattered across the Badlands. Every layer of sediment tells part of the story. Every fossil fragment adds another piece to the puzzle. When you hold a fragment of Tyrannosaurus tooth or examine the intricate pattern on a Triceratops frill, you're not just looking at prehistoric artifacts. You're touching the physical remains of the most extraordinary terrestrial ecosystem our planet has ever produced. What makes Hell Creek truly remarkable isn't just what it preserves, but how it preserves it. The specific geological conditions that created this formation allowed for exceptional fossilization that captures not just the hard parts of ancient organisms, but sometimes their soft tissues, their behavior, and even their final moments. We can see bite marks that tell stories of predator-prey interactions. We can examine coprolites that reveal ancient diets. We can study growth patterns in bones that show us how these creatures lived and aged. The techniques paleontologists use to extract information from Hell Creek fossils continue to evolve at a breathtaking pace. Advanced imaging technologies can now peer inside fossils without damaging them, revealing internal structures that were previously invisible. Chemical analyses can determine what these animals ate, where they lived, and how they interacted with their environment. Computer modeling helps us understand how they moved, how they hunted, and how they survived in their ancient world. Each new analytical breakthrough opens previously locked doors into the Hell Creek ecosystem. Recent discoveries of preserved melanosomes have allowed scientists to determine the actual colors of some dinosaur feathers. Isotope analyses reveal migration patterns and seasonal behaviors. Biomechanical studies show us exactly how powerful a Tyrannosaurus bite really was and how fast these giants could actually move. But perhaps the most important lesson Hell Creek teaches us is about the interconnectedness of all life. This wasn't just a world of isolated species competing for resources. It was a living web of relationships where every organism, from the mightiest predator to the smallest decomposer, played crucial roles in maintaining the whole system. The loss of any component could trigger cascading effects throughout the entire community. Understanding these ancient relationships helps us better appreciate the complexity of modern ecosystems and the importance of conserving biodiversity in our contemporary world. The Hell Creek extinction demonstrates that no species, no matter how successful or dominant, is guaranteed survival when faced with catastrophic environmental change. Even Tyrannosaurus rex, the most powerful terrestrial predator in Earth's history, couldn't survive the collapse of the ecosystem that sustained it. As we face our own environmental challenges, the lessons from Hell Creek become increasingly relevant. This ancient world shows us what's possible when conditions allow life to flourish, but also demonstrates how quickly complex systems can collapse when those conditions change too rapidly. The balance between productivity and vulnerability that characterized Hell Creek continues to influence ecosystems today. The Hell Creek Formation will continue yielding new discoveries for generations to come. There are countless fossils still waiting to be found, countless stories still waiting to be told. Each field season brings new specimens that add to our understanding of this remarkable world. Each laboratory analysis reveals previously unknown aspects of ancient life. The legacy of Tyrannosaurus and its Hell Creek kingdom lives on in multiple ways. In the fossil record that preserves their world for future study, in the descendants of the survivors who inherited the post-extinction Earth, in the ecological principles that continue to govern natural systems, and in the sense of wonder and curiosity that drives us to understand our planet's incredible history. The tyrant king may have fallen 66 million years ago, but its story continues to inspire and educate us about the magnificent complexity of life on Earth. Through studying the Hell Creek ecosystem, we gain not just scientific knowledge, but profound